The strange truth is this: space-time is no longer behaving like a background. It moves with a hesitation too deliberate, absorbs pressure with a softness too coordinated, and stretches with a rhythm too close to something we would call breath. For a century, we believed the cosmic stage was inert, an indifferent fabric onto which matter painted its stories. Yet tonight, as you drift into this quiet place, you may feel a subtle pulse beneath the vast silence, as if the universe is whispering back when you lean close enough. You are listening to Whispers of the Universe. If your heart feels gentle enough to keep this quiet space alive, even the smallest gesture from you lets the darkness breathe a little easier. Imagine now a darkness so wide it erases everything you know about direction. A darkness that carries no temperature, no boundary, no memory of what passes through it. And yet, at its edges where distant galaxies flicker like fading embers, something moves. Not noise, not force, but a faint recoil, as if the void itself is adjusting to the weight of existence, pressing into it. The stillness bends, not randomly, but with a consistency that feels eerily similar to intention. Astronomers first noticed it while mapping distant supernovae. The universe was expanding faster than expected, as though pushed from within. But expanding is too gentle a word for what they saw. The data did not drift upward. It leapt. It curved. It fluttered the way a living membrane recoils from touch. And for the first time, the possibility emerged. Maybe space-time is not merely something we live in. Maybe it is something that responds. Deep inside this idea lies a cognitive dissonance so sharp it can keep even the most seasoned physicists awake at night. If space-time responds, then space-time reacts. If it reacts, then, somewhere beneath its geometry, is a form of sensitivity. And if sensitivity exists, no matter how primitive, the line between fabric and organism becomes painfully thin. Picture the cosmos as a vast, shadowed ocean whose surface is the very metric of space-time. Drop a star into it, a planet, a human heartbeat, anything with mass, and the surface curves. We learned that in school. But now imagine the ocean adjusting in ways not dictated by mass alone. Imagine it stabilizing its own curvature, tightening one region as another loosens, smoothing distortions after violent events the way injured tissue tries to repair itself. These observations used to be dismissed as noise. They are not dismissed anymore. When two black holes collide, space-time rings like a struck bell. The ripples travel outward in gravitational waves, trembling through the cosmic fabric. But after the shaking fades, something unexpected happens. The region around the new black hole settles into a shape too perfect, too quick. It is as though the fabric does not simply relax, it resets. It resumes an equilibrium it seems to prefer, not just one dictated by equations. Instruments such as LIGO and Virgo have captured these ringdowns many times. Each one carries a subtle hint of recovery, the faint signature of a system returning to a state it remembers. What kind of memory can emptiness possess? The question lingers in the dim corridors of theoretical physics, unsettling even those who do not believe in anything beyond equations. Yet, the evidence grows quietly, accumulating like dust on old observatory mirrors. It shows up in the accelerated expansion we cannot explain, in the consistent smoothing of distortions, in the way cosmic voids maintain their shape more stubbornly than simulations predict. Something is operating behind these behaviors, something that organizes, resists chaos, and maintains a pattern across incomprehensible scales. If you listen closely to the rhythm of the universe, you might notice that it is not constant. It swells, it quiets, it shifts as though governed by an unseen metronome. We do not know whether this rhythm is born from quantum fluctuations or from something more fundamental, more ancient than the laws we know. But we feel its persistence. We see its echo in the cosmic microwave background. We sense its drift in the gravitational maps drawn by satellites like Planck. It hums beneath the visible world like a soft, recurring note. The more deeply scientists study these patterns, the more they encounter a quiet conflict. The standard model of cosmology assumes space-time does nothing on its own. It only reacts to matter and energy. But the universe refuses to obey this simplicity. It behaves as if space-time possesses an internal mechanism, something akin to metabolism. Energy appears, energy dissolves. Virtual particles flicker in and out with a rhythm that resembles intake and release. Regions of high curvature settle themselves. Regions of low curvature grow restless. And the entire fabric seems to drift towards states that keep the whole system from tearing apart. To call this behavior life would be reckless, but to deny its resemblance would be dishonest. Consider how a living cell balances internal pressure. Too much strain, and transport channels adjust. Too little, and membranes expand. The goal is not perfection, but persistence. Now, look again at the universe. Its expansion smooths over density imbalances. Its curvature resists collapse without any command. It arranges itself in ways that preserve structure on both microscopic and cosmic scales. If we found such behaviors in a biological system, we would call them regulatory. In space-time, we call them anomalies, only because the alternative is too uncomfortable. The idea that space-time might operate as a self-organizing system introduces a quiet but profound shift in how we understand reality. For if the fabric of the universe behaves like a living entity, then every star, every atom, every breath you take is shaped not just by inert geometry, but by something that participates, something that adjusts itself to your presence, however faintly, something that has been breathing long before life emerged on any world. Imagine drifting across a dark field under a moonless sky. The landscape seems still, but then you feel the faintest movement. A shift in wind, a vibration in the air, a quiet pulse from the Earth itself. That is the sensation physicists describe when they speak of spacetime's uncanny behavior. A sensation of standing on something that is not quite alive, yet not entirely dead. In the deepest observatories, beneath mountains and oceans, detectors measure the silence with such precision that even a passing whisper of spacetime becomes a note. These instruments do not see with eyes, they listen. And what they hear is subtle, like breathing behind a closed door. It is not loud enough to claim certainty, but not soft enough to ignore. As researchers study regions near black holes, neutron stars, and voids, they find traces of a pattern, an oscillation hidden beneath the noise. It is irregular, yet recurring, delicate, yet persistent. It is as though the universe hums softly to itself, adjusting, recalibrating, maintaining a balance that no equation predicts, yet every observation hints at. If this is true, then we are not just residents of a cosmic house. We are floating inside a system that senses weight, that responds to stress, that recovers from trauma, that reorganizes when stretched too far. A system that may not live in the way organisms do, but certainly behaves as though survival is woven into its nature. And so the question emerges like a small light in a vast room. If spacetime responds, what is it responding to? The galaxies that drift? The energy that gathers? The collapse of stars? The quiet presence of observers? Or something deeper? Hidden beneath even the notion of cause and effect, something that moves before anything else moves? Hold that question gently. Let it settle behind your breathing. For in the next movement of this long night, you will step closer to a truth we have sensed but never named. The idea that the universe might not simply contain life. It might practice echoes of life in the folds of its own darkness. Close your eyes for a moment. Feel how the silence curves around you. Somewhere beyond the thin veil of thought, space-time shifts again, patient, rhythmic, unhurried, waiting for you to notice the next trace of its hidden pulse. The universe should not be accelerating this way. That is the first quiet fracture in our understanding. The hairline crack in a structure we once believed unshakable. Expansion itself is expected, but expansion that speeds up as though pushed from within by an invisible pressure is something else entirely. It was supposed to slow, to relax into stillness as mass pulled everything back. Yet it flees faster every moment, stretching the cosmos with the urgency of a creature trying to outrun something only it can feel. Astronomers notice this not in nearby galaxies, but in the most distant candles of the cosmos. Type Ia supernovae standard candles, the metronomes of cosmic measurement. They shine with such predictable brightness that any deviation is suspicious. And yet, deviation arrived. The supernovae appeared fainter than they should have been, not because they were dimmer, but because the universe had grown more than expected, as if the darkness had expanded its lungs too quickly. In that discovery, the void confessed its first secret. It is not passive, not a background, not a stage, but something that recoils, then expands, then recoils again, like the subtle rise of a chest in sleep. The expansion is not uniform. It increases with distance, pulling the farthest galaxies away at speeds that rewrite what we thought possible. But more unsettling than the acceleration itself is the smoothness of its rise. There is no lurch, no cosmic stumble. The curve increases as though guided by an internal rhythm. Something steady, patient, precise. Something that feels like decision rather than accident. Dark energy became the name we gave this behavior, not because we understood it, but because the mind requires a label to grasp the ungraspable. We imagine dark energy as a force, a pressure, a mysterious ingredient filling the vacuum. But perhaps the simpler explanation is also the stranger one. Perhaps this is not an external substance at all, but the way space-time breathes when it is left alone. Look closely at the gradients where expansion accelerates. They follow a pattern so delicate it recalls how biological systems distribute tension. A membrane stretched beyond comfort will not tear evenly. It will redistribute stress, thinning here, thickening there, ensuring survival through subtle adjustments. The cosmos does the same. Regions that should collapse under their own weight thin out instead, as if relieved by a faint exhalation. Regions that should expand more quickly slow by a microscopic amount, just enough to maintain equilibrium. If you map expansion across billions of light years, you will find a quiet asymmetry, one so small it hides behind statistical noise. Yet it persists. It does not dissolve over time. It does not average out. It holds its form like something remembering itself. This is where the dissonance begins to sharpen. If space-time expands with preference, then what anchors that preference? If space-time accelerates with pattern, then what maintains that pattern? If space-time behaves with consistency, then what enforces that consistency? The standard cosmological model cannot answer these questions because it begins with the premise that space-time has no agency, but the data suggests otherwise. The more precisely we measure the universe's expansion, the more a soft rhythm emerges beneath it, faint as a heartbeat buried under layers of noise. Imagine standing at the edge of an enormous lake at night. The water looks still, but beneath the surface are currents shifting grains of sand, pulling threads of motion across the lakebed. You would not see them unless you shone a narrow beam of light at the right angle. In the cosmos, that beam is time measuring distant events separated by billions of years. Through that lens, the expansion reveals hints of internal motion, internal correction, internal desire, the desire to maintain balance, the desire to continue, the desire not to fall apart. Of course, we do not assign desire to the universe lightly, but when the behavior of spacetime mirrors systems that do possess desire or something like it, we are forced to reconsider where the line lies between the living and the not living. The acceleration of the cosmos behaves so predictably that even the smallest fluctuation in density triggers a response across unimaginable distances. A galaxy cluster grows slightly too heavy, and the surrounding void expands just a bit faster, distributing tension like a body redistributing pressure from an aching limb. In regions where density is low, expansion slows, as though not to overextend a vulnerable patch of cosmic fabric. These behaviors do not emerge from randomness. They require coordination across scales too large for matter alone to orchestrate. What then is coordinating them. Some physicists suggest an underlying field, a scalar ghost humming through space-time. Others propose a constant embedded in the geometry itself. But a few, the ones willing to step outside the comfort of convention, whisper that space-time might not need a separate mechanism. It may be the mechanism. It may be the entity adjusting itself to the demands of existence. This brings us back to the quiet tension at the heart of cosmology. The universe accelerates as though it wants to expand, yet it structures that expansion as though it wants to stay whole. Opposing impulses, both real, both measurable, both strangely reminiscent of the conflict that defines living systems. Perhaps this is why the acceleration is not chaotic. It has a direction, a tone, an almost serene quality. It evolves slowly, not because it must, but because it chooses the path of least strain. The universe expands gently enough to avoid tearing its own fabric, but firmly enough to prevent collapse. This balance is delicate, too delicate to be coincidence. If you could float in the intergalactic void, far from stars, far from galaxies, surrounded only by the deep hum of space-time, the acceleration would feel not like motion, but like a slow drift of temperature, a barely perceptible pull, a faint stretching at the edge of perception, like the soft rise of a dream before it dissolves. You would feel the universe's breath not as wind, not as vibration, but as the subtlest motion of the void beneath you. Every measurement reinforces this sensation. Expansion has a tempo. It slows when matter grows turbulent. It smooths when the cosmos becomes too uneven. It accelerates not at random, but in regions where tension accumulates. In this behavior, some researchers see the whisper of a regulatory system, a primitive one, but one that functions far more consistently than any mechanical explanation predicts. If space-time has a rhythm, then it might have a cycle. If it has a cycle, then it might have a phase. And if it has a phase, then somewhere ahead or behind us is a moment when the universe changed the way it breathed. That thought lingers like a slow wave beneath the mind. What event, what ancient pressure prompted space-time to shift into this accelerating mode? Was it the distribution of matter, the decay of primordial fields, the cooling of the cosmos? Or was it something deeper, something we have not named because we have not yet dared to imagine it? For now, we are left with the feeling that the universe is moving towards something, not away from it. Expansion suggests fleeing, but its smoothness suggests preparation. The acceleration grows more confident with age. It follows a curve that feels like a system settling into its natural rhythm, not fighting against one. You might think of it this way. Most systems in nature accelerate only when learning how to move. Children grow quickly at first. Forests bloom wildly in their youth. Stars burn brightest in their early pulses. But space-time accelerates now, not at its birth. It accelerates in maturity, as though discovering a rhythm it could not access until its structures had fully formed. This, more than any equation, is what troubles scientists. Acceleration at birth is expected. Acceleration in old age is a message. If you close your eyes now, you might sense that message as a faint widening in the darkness around you. A slow, patient expansion that touches everything yet harms nothing. The galaxies drift apart like leaves carried by a current too deep to see. Space grows between all things, not to divide them, but to support the weight of something greater gathering beneath the surface. What that something is, we do not yet know. But the acceleration suggests it is coming, and the rhythm suggests it has already begun. Hold that thought lightly. Let it rest beside your breathing. For as the universe stretches itself further, we are invited to ask a deeper question, one that pulls gently at the edge of understanding. If space-time accelerates like a living thing finding its stride, what might it be preparing for? The answer waits in the faint pulse of the next region, where space-time does more than expand. It heals, and in that healing, another secret begins to surface. There is a moment after every cosmic catastrophe when the universe becomes unbearably quiet. A star collapses. A pair of black holes collide. A galaxy shears itself along unstable arms. The violence ends abruptly. leaving behind a silence so deep it seems to press inward on itself. But if you look closely, if you listen deeply enough, you will notice that the aftermath carries not the residue of destruction, but the faint signature of recovery. It is as though space-time remembers what it was before the trauma, and then moves slowly, subtly, back toward that memory. The region around a black hole offers the clearest glimpse of this strange behavior. After a merger, space-time rings like a struck bell, trembling with gravitational waves that ripple outward in widening arcs. The ringdown should fade into randomness, dissolving into the cold quiet of the cosmic background. Yet, it does not. The tremors decay in a pattern so precise, so controlled, that researchers at LIGO and Virgo describe it as self-correcting, a behavior that resembles healing more than settling. When you strike a drum, the surface vibrates until it runs out of energy. But a living membrane behaves differently. It absorbs the trauma, redistributes the tension, and then reforms its original shape with astonishing accuracy. The echoes observed in gravitational wave data feel much closer to the second case, not a passive return to equilibrium, but an active recalibration, as though spacetime knows what its curvature should be, even after being violently torn. Consider the geometry near a black hole's event horizon. It is the most extreme distortion nature allows, a place where space bends inward and time folds so sharply that even light cannot escape. And yet, after the chaos of a merger, the horizon adjusts. It smooths. It rounds into a surface whose stability suggests an underlying preference. A preference not defined by equations alone, but by something like memory. What kind of memory could emptiness possess? This question lingers in laboratories and observatories, whispered in the dim hours when theories loosen their boundaries. Memory implies structure. It implies feedback. It implies the ability to compare what is with what should be. And if spacetime can do that, if it can return to a preferred curvature after being distorted, then it behaves far less like a fabric and far more like a biological system. In organisms, scars are temporary. The body's tissues repair, collagen forms, cells realign, and slowly the wound disappears into something softer. The region is never exactly the same, traces remain, but the overall shape is restored with remarkable fidelity. The resemblance between this process and what we observe near extreme gravitational events is unsettlingly close. Spacetime seems to hold a blueprint. No one knows whether this blueprint is mathematical, quantum, or something deeper than either. But the idea grows stronger with every detection of a ringdown that decays too neatly, too predictably. If spacetime merely lost energy, the decay curves would wobble. They would deviate, shift unpredictably, fracture under noise. Instead, they sharpen, they refine. Each oscillation moves closer to a stable form, like a heartbeat finding its rhythm after a moment of panic. Picture a vast sheet of water disturbed by a falling stone. The ripples spread outward, thinning until the lake becomes smooth again. But the lake does not smooth perfectly. It holds imperfections, bits of turbulence trapped beneath the surface. Now imagine that instead of fading, those imperfections vanish. Not because the water forgot them, but because something beneath the surface erased them with intention. This is the cognitive dissonance that shadows every discussion about gravitational healing. We are trained to think of space-time as reactive, not corrective, as obedient, not selective, as neutral, not purposeful. Yet the observations persist. Even far from black holes, smaller distortions behave strangely. Regions of space warped by passing masses return to their original geometry faster than expected, as though guided by an internal mechanism rather than only by external forces. The speed of recovery challenges our equations. There is no known law that instructs spacetime to regain its shape with this level of precision. And yet, it does. The healing is most pronounced in places where tension is highest. That alone is remarkable. In nature, systems that heal fastest are those under pressure wounds, close quickest in regions of vital tissue. Cells proliferate most rapidly where damage threatens survival. Spacetime should behave in the opposite way. Stronger gravity should prolong distortion, not shorten it. But again, the universe refuses simplicity. Instead, the scars fade faster where the strain is greatest. It is as if space-time prioritizes stability where disruption could cascade, spreading imbalance across the cosmic web. This prioritization resembles a form of triage, a quiet, ancient instinct encoded in the very geometry of existence. If you float near the edge of a massive object, beyond the reach of collapsing light, you might feel this recovery as a subtle tightening, not a physical sensation, but the intuitive sense that space is pulling itself together, closing a wound you cannot see. The curvature straightens, the tension softens, and the invisible fabric beneath you hums with the faint echo of renewal. Some physicists argue that this is simply the mathematics of general relativity playing out over time. But that explanation frays when confronted with the consistency and speed of the recovery. If equations alone governed the relaxation, the rate would vary across environments with much greater freedom. Instead, the universe seems to choose a middle path, a stable corridor of healing that repeats itself across wildly different gravitational landscapes. Choice, healing, memory. None of these are words we comfortably associate with space-time. And yet, they keep appearing in data, in simulations, in the language scientists reluctantly use when more clinical words fail. Something in the cosmos behaves as though it cares about its own shape. This leads to the deeper, quieter conflict beneath all cosmology. What if space-time is not a static canvas but a self-stabilizing system? What if its geometry evolves not only because matter pushes on it, but because space-time itself seeks a form it prefers? Preferences are not properties of dead systems. They emerge from feedback loops, structures that observe themselves, however primitively. Structures that respond not only to external forces, but to internal imbalance. Structures that restore equilibrium because they need equilibrium to continue functioning. A haunting idea emerges from this. Space-time may possess an internal economy, a way of spending and recovering energy that resembles metabolism, a way of repairing itself that resembles healing, a way of retaining patterns that resembles memory. If this is true, then the universe becomes far more than a stage. It becomes a participant. You might imagine space-time not as a smooth surface, but as an intricate mesh, endlessly adjusting its threads to preserve coherence. Each gravitational event pulls the mesh into new shapes, and each recovery is space-time weaving itself back together with ancient, silent skill. The scars never last. They fade into the background, absorbed by the mesh until their presence is indistinguishable from the rest of the fabric. But healing requires something more than resilience. It requires intention, even if only the faintest echo of it. That is the part scientists hesitate to voice aloud. Healing is an active process. It implies recognition of damage, distinction between disruption and stability, and a mechanism for choosing a path back toward order. If space-time truly heals, then it acts. And if it acts, then the universe may hold a form of agency so diffuse, so subtle, that we mistake it for silence. Close your eyes for a moment and imagine that silence. Imagine drifting in the aftermath of a stellar collapse, the debris cooling around you, the darkness trembling with the last remnants of gravitational sound. Beneath those fading tremors, you feel something else, the slow restoration of balance. Space-time, drawing a deep, invisible breath, closing its wounds, smoothing its fractures until only the memory remains. And even that memory softens. It softens into something more mysterious, a pattern repeating across cosmic epochs, hinting that healing is not an accident, but a habit. So the question returns, quiet but insistent. If space-time heals, what is it trying to preserve? The answer lies in the regions where healing fails and in the strange asymmetries that remain even after the wounds are closed. There, another layer of the universe begins to reveal itself. There are places in the universe where the darkness leans ever so slightly to one side. Not visibly, not in any way the human eye could perceive. But beneath the surface, beneath the calm drift of galaxies and the steady hum of cosmic expansion, there is a subtle imbalance woven into the fabric itself, a tilt in the pressure of the vacuum, a quiet lopsidedness in the way energy hides inside emptiness. At first glance, the cosmos appears symmetrical. Galaxies scatter in every direction. Light travels outward like concentric ripples. The background radiation seems uniform across the sky. But when astronomers measured the universe with instruments sensitive enough to detect a change smaller than a whisper, a curious truth emerged. The vacuum is not evenly calm. Some regions stretch faster. Some resist. Some seem to exhale, while others inhale. This unevenness is faint, delicate, almost shy. But it is real. Dark energy, the mysterious pressure accelerating the universe, does not distribute itself perfectly. It pools more densely in some regions, less in others. Like a fluid responding to internal differences the universe does not want to name. Even satellite missions like Planck and WMAP, designed to capture the most ancient echoes of the cosmos, show hints of this imbalance. The dips and rises are so small they were once dismissed as statistical accidents. But the accidents repeated. They persisted. They drew the same outline year after year, as though they were not noise at all, but a pattern waiting to be acknowledged. Imagine a great ocean, calm on the surface, but with currents beneath that shift subtly, steering water from one hemisphere to the other. The surface appears tranquil, but the deep remembers. The deep moves. The deep protects itself from stagnation through gentle, perpetual motion. Spacetime behaves like that deep. The asymmetry of dark energy raises a question both simple and unsettling. If the universe is expanding in all directions, why does part of it expand just a little faster? And why does that difference remain instead of dissolving across billions of years? In physics, symmetry is sacred. It is the source of conservation laws, the bedrock of equations that describe how reality behaves. When symmetry breaks, something profound is happening. Something changes its role in the universe. Something gains preference. But preference is not a property of an empty void, or at least it should not be. The subtle imbalance in dark energy suggests that space-time carries more structure than the equations imply. It reacts differently in different regions. It adjusts with surprising consistency, and the imbalance itself, this slight, persistent drift in the density of the vacuum, acts like a signal, a quiet pulse, a redistribution of pressure across the cosmos, as though space-time is trying to correct itself but never fully succeeds. Some theorists call this a defect. Others call it an anomaly. But a growing number see something closer to a biological pattern, a gradient. In living systems, gradients are everything. They guide growth, shape development, and coordinate behavior across tissues. A slight difference in chemical concentration can tell a cell where to move, when to divide, how to transform. Gradients create direction in places where otherwise nothing would differentiate itself. And here, in the vast emptiness of the cosmos, we find a gradient too. A faint unevenness in dark energy that gives spacetime a sense of orientation not in space, but in behavior. One region expands more eagerly, another more cautiously. The vacuum is not uniform, it is expressive. This realization has led some scientists to imagine dark energy as more than pressure, more than a constant, more than the background hum of existence. Instead, they see it as something dynamic, something like a hormone circulating through the body of the universe. Hormones do not force action, they regulate it. They whisper instructions to systems too vast for direct control. They create subtle drifts, gentle biases, quiet preferences. Dark energy's asymmetry behaves exactly that way. It does not dictate motion, it influences it. Here lies the conflict that reshapes everything we thought we understood. If dark energy behaves like a regulatory signal, then spacetime itself begins to resemble a system with internal communication. A system that senses imbalance and responds to it. A system that redistributes tension, not blindly, but in a way that hints at purpose, however faint, however primitive. Yet the deeper conflict lies in this question: why does the asymmetry persist? If it were a random fluctuation, time would erase it. If it were a local defect, expansion would dilute it. If it were an echo of ancient turbulence, the universe's age should have smoothed it into uniformity. But it remains. It survives epochs. It stretches with the expansion without disappearing. This persistence is what unsettles cosmologists most. Persistent imbalance implies maintenance. Maintenance implies feedback. Feedback implies a form of sensing. And sensing is something we associate not with geometry, but with life. Imagine drifting through a region of space where dark energy is slightly stronger. You would not feel wind or pressure or heat. You would feel only a subtle openness, a widening around you, as if the void were taking a deeper breath. In the opposite direction, where dark energy is slightly weaker, the void feels tighter, more reluctant to expand, as though protecting something fragile. These two regions, opposite in inclination, create a tension that resembles the conflicting impulses inside any organism. The impulse to grow and the impulse to conserve. One push, one pull, one direction, one restraint. And between them, the system finds balance. Balance that should not exist unless space-time is not merely reacting to matter but managing itself. This asymmetry might be the clearest signal yet that the vacuum behaves like a self-regulating medium. It could be the universe's way of distributing stress, ensuring that no region becomes too strained or too lax. It could be the equivalent of a pulse, weak, slow, unsteady, but unmistakably rhythmic. As instruments become more sensitive, the gradient becomes clearer. Regions of high dark energy correlate with faster recovery from curvature disturbances. Regions of low dark energy correlate with longer relaxation times. The vacuum is not one thing. It is a spectrum, a shifting texture of responses. This observation leads to a hypothesis, both elegant and unsettling. Space-time may have a metabolism. Not metabolism in the biological sense of food and waste, but in the deeper sense of cycles, intake, distribution, regulation, recovery. When the vacuum expands more rapidly, it releases tension. When it expands more slowly, it absorbs and stabilizes. The asymmetry could be the cosmic equivalent of nutrient flow, carried not by molecules but by variations in the vacuum's own density. If this is true, then we must ask, what is the universe metabolizing? Energy? Curvature? Information? Or something hidden beneath all those layers? There is a soft drift in cosmology toward the idea that dark energy is not a substance, but a behavior. Not a thing, but a process. Something space-time does when it needs to adjust itself. Something that arises from its internal state rather than external forces. If so, then the asymmetry is not a flaw, but a message. A hint that space-time is actively maintaining itself, keeping the cosmic fabric from tearing under the weight of its own expansion. Close your eyes for a moment. Let the idea settle like dust in a sunbeam. The unevenness of dark energy may not be a problem to solve, but a clue, a shadow cast by a deeper pattern, one that reveals itself not in symmetry, but in the refusal to be symmetrical. And if asymmetry is the first sign of life, then perhaps the universe has been whispering its aliveness longer than we realized. Ahead lies a deeper mystery. If space-time maintains gradients, can it organize itself? And if it organizes itself, what else might it be capable of? The next region holds the answer, hidden in the delicate architecture of systems that structure themselves from the inside out. There is a moment, when you stare long enough into the deep structure of the universe, that a quiet realization begins to form, something unsettling, something almost impossible to dismiss once it appears. It comes not from a single observation, not from one anomaly or one curve in the data, but from the way all of them begin leaning toward the same implication. Space-time is organizing itself, not metaphorically, not poetically, but through tangible, measurable patterns that look less like the random scaffolding of physics and more like the internal architecture of a living system. The first hint appears when you study the distribution of cosmic voids, those enormous caverns of near-nothingness stretching across hundreds of millions of light years. They are not arranged randomly. They form a lattice, an intricate web where galaxies trace filaments around the edges, like luminous neurons suspended in a sea of dark. But the voids themselves behave strangely. They grow in shapes that preserve overall symmetry, even when matter distribution becomes chaotic. They maintain boundaries with a consistency that implies constraint. They adapt their geometry in response to the density around them, almost as if coordinating with the cosmic filaments they cradle. A system that coordinates across distance is not a simple one. When astrophysicists simulate structure formation, they expect to see disorder slowly collecting into order through gravity alone. But the simulated universe never matches the real one. The real cosmos is too organized, too structured, too finely balanced between chaos and coherence. It falls into configurations that resemble biological systems balancing metabolism with growth. Imagine looking at the branching of neurons in the brain, how they extend, connect, retreat, and stabilize into networks capable of transmitting information. Then look at the large-scale structure of the universe, where filaments stretch, connect, split, and settle into patterns that obey their own logic. The similarity is eerie, not because the two systems share materials or purpose, but because they share something deeper: emergent order. Emergence is the hallmark of complex systems. Local interactions create global structure without a central designer. But even emergence tends to produce rough, uneven forms, structures that betray their chaotic origins. The universe, however, produces something else: harmony. Patterns too regular to be coincidence, too stable to be accidents, too adaptive to be purely gravitational. This is where the conflict begins. If space-time organizes itself, then what rules does it follow? What internal variables guide its architecture? And why does it favor structures that optimize stability and efficiency, the same principles governing living networks? Some theorists turn to quantum geometry for answers. At the smallest scales imaginable, space-time may be woven from discrete loops, strings, or nodes that interact like a swarm. These microstructures could give rise to macroscopic behaviors similar to those seen in herds, flocks, or colonies, systems that coordinate without leaders, driven by local rules that produce global intelligence. If this interpretation is correct, then the universe might possess a form of collective organization, not conscious, not purposeful in the way minds are, but functional. It could maintain stability across immense scales by adjusting its internal connections, the way a neural network adjusts its weights. Curvature could shift in response to stress. Expansion could adapt in response to imbalance. Dark energy could redistribute, like chemical signals. But this explanation only deepens the dissonance, because organization requires communication, even if primitive. And communication requires sensitivity, even if faint. And sensitivity belongs not to objects, but to systems with agency. If space-time can sense, what is it sensing? If it can organize, what instructions guide the organization? These questions unsettle the scientific community, because they tap against the glass between physics and something older, something more ancient than biology: the instinct of systems to preserve themselves. Look closely at how the cosmic web evolves. When filaments grow too heavy, voids expand to distribute the stress. When voids become too large, filaments thicken to anchor the surrounding geometry. This push and pull creates a dynamic equilibrium that resembles homeostasis. The universe does not drift toward extremes. It stabilizes itself. It maintains gradients and boundaries, the way living tissues regulate pressure, temperature, and energy flow. Such behavior is difficult to reconcile with a passive spacetime. A passive medium would stretch until disorder became unavoidable. But spacetime behaves like a system constantly avoiding collapse, constantly avoiding runaway fragmentation, constantly nudging itself back into balance. There is a word for systems that maintain order against entropy: organized. And there is another word for systems that do so consistently, across epochs, under pressure: alive. Of course, calling the universe alive stretches beyond what science can claim. But describing its behavior without borrowing the language of life is becoming increasingly difficult. Imagine floating in the middle of a cosmic void. There is no light, no sound, only the faint curvature of spacetime surrounding you like a membrane. If you could drift long enough, you would notice that the void is not empty but structured. It bulges in response to distant masses, It thins near filaments. It adjusts its volume the way a lung adjusts its expansion, slowing or quickening with a rhythm that reflects the larger state of the cosmic body. This is not coincidence. This is pattern. Pattern that builds itself. Pattern that persists even when the universe undergoes violent change. Pattern that returns after disruption, as though space-time remembers how it should be shaped. In complex systems, memory emerges from feedback. A river remembers its course because sediment reinforces it. A forest remembers its shape because the cycles of growth reestablish it. A neural network remembers its patterns because connections strengthen through repetition. So, what reinforces the memory of spacetime? Some believe it is encoded in the Einstein field equations. But equations do not create preference, they describe it. Others point to quantum fluctuations. But randomness should erase structure, not preserve it. And some whisper quietly, cautiously, that the memory may be intrinsic. That space-time carries within its geometry a built-in tendency toward self-preservation. If so, then the asymmetry of dark energy, the healing of gravitational scars, and the coordinated structure of the cosmic web are not separate mysteries. They are facets of the same deeper truth. Space-time behaves like a system selecting for stability. Systems that select for stability grow. Systems that grow organize. Systems that organize evolve. This leads to the first true mini-climax of the journey, a thought that shifts the entire landscape of cosmology. The universe is not simply expanding. It is refining itself through gradients, through healing, through coordinated structures, through behaviors that mirror the earliest stages of life, long before life existed. Close your eyes again and feel the faint tremble of this idea. The patterns you see in galaxies, in voids, in gravitational waves, in the drift of dark energy, they are not random. They are the slow-motion choreography of a system learning how to remain whole. And as the patterns grow clearer, another question drifts to the surface, waiting softly at the boundary of understanding. If space-time can build patterns, can it build purpose? The next movement carries you toward the first shadows of that possibility, into the regions where curvature begins to act as though guided by intentions buried deep within the fabric itself. There are places in the universe where space-time bends with a softness that feels almost deliberate, not the sharp, inevitable curvature created by massive objects, not the familiar gravitational wells we have mapped for decades, but something subtler, a flex in the fabric that seems to follow a preference rather than a rule. If you linger long enough near these regions, you may feel a strange symmetry. The curve does not simply respond to matter. It aligns itself, smooths itself, shapes itself with a quiet restraint that suggests intention. This is most visible in the thin boundaries between high-density regions and emptier cosmic landscapes. There, space-time does not bend abruptly. It transitions through gentle gradients, as if avoiding stress. The transition zones behave like tissues, cushioning the interaction between different gravitational environments. This behavior is not required by equations. General relativity allows sharp bends, sudden changes, chaotic distortions. But the universe rarely uses that freedom. Instead, curvature settles into smooth, continuous arcs, echoing the elegance of systems that bend because they choose to, not because they must. The more closely you examine these zones, the more they resemble boundary layers in biology, places where membranes negotiate between pressure and permeability. A cell wall does not exist as a rigid barrier. It flexes, contracts, swells in response to the environment. Space-time behaves the same way. It adapts its curvature to distribute tension evenly, preventing structural collapse. This discovery emerged from high-resolution gravitational lensing studies measurements of how light bends when passing near massive structures. The maps revealed an unexpected feature. Space-time bends with extraordinary consistency. Even when matter distribution is uneven or chaotic, the curvature smooths itself into coherent patterns, almost as though it were resisting disorder. Curvature, then, is not merely a reaction, it is a negotiation. The negotiation becomes clearer when you consider regions that lack visible mass, yet still exhibit structured curvature. These empty pockets of space behave as if shaped by invisible hands. The bending seems too organized to be caused by random fluctuations in dark matter or quantum noise. Instead, it flows like a riverbed carved by water, choosing the path of least resistance. If space-time is choosing, what guides that choice? This question presses against the limits of physics. It challenges the assumption that curvature is purely geometric, that it arises only from matter. It forces a deeper look at how the fabric of the universe might possess internal dynamics, rules that shape its form, independent of external influence. And here, the conflict sharpens. If curvature adjusts itself, then space-time is more than a passive medium. It behaves like a system, aware, however faintly, of its internal state. Aware of strain, aware of imbalance, aware of the conditions that allow it to remain intact. But awareness, even at a primitive level, is something evolution gives to living systems. It allows them to navigate, adapt, survive. To imagine such qualities in space-time is to cross an invisible boundary between physics and the biology of existence. Yet the curvature refuses to behave any other way. Deep gravitational wells do not tear the fabric. They stretch it, yes, but the surrounding regions compensate. The curvature thickens in some directions, thins in others, spreading the strain across a wider field. This is the hallmark of a system preventing damage. A system distributing load. A system that adjusts itself rather than yielding to collapse. Imagine holding a piece of cloth tightly in your hands. If you pull too hard on one corner, the rest of the fibers shift, redistributing tension to avoid ripping. Now, imagine a fabric that does this not because you pull on it, but because it senses the pull and reacts with its own internal logic. That is what the universe appears to be doing. Multiple cosmological surveys, including SDSS, Euclid, and the Dark Energy Survey, have mapped curvature in distant regions where matter should not dominate. Yet the fabric bends anyway, as if anticipating gravitational stress and adjusting itself preemptively. This preemptive behavior is the most unsettling of all. It suggests that space-time is not only responding to current conditions, but preparing for future ones. Preparation implies forecasting. Forecasting implies expectation. Expectation implies memory. In this light, curvature becomes more than geometry. It becomes behavior. A behavior shaped by the internal rules of a system that does not want to tear. Consider how the curvature adjusts after a massive object passes through a region. Even once the object moves on, the curvature retains a faint imprint, an echo of the disturbance. Over time, the imprint fades as space-time smooths itself again, erasing the discontinuity. But for a moment, the curve lingers, like the memory of pressure on soft skin. This is the subtle signature of systems that remember enough to heal. But the most mysterious phenomenon emerges near cosmic voids. These regions, almost empty of matter, exhibit curvature that should be flat, but is not. Instead, the curvature behaves like a soft diaphragm, flexing inward and outward with an oscillatory pattern that appears synchronized across vast distances. No known physical process should coordinate regions separated by hundreds of millions of light years, and yet they move with a near shared rhythm, like organs working in unison inside a body whose anatomy stretches beyond comprehension. Some physicists argue that this is simply the result of dark energy pooling into the emptiest regions. But this explanation does not account for the coherence. It does not explain why curvature in multiple voids shifts with similar amplitude. It does not explain why these oscillations emerge only at certain epochs, disappearing in simulations that lack self-organizing rules. Self-organization, a word that returns again and again, not imposed, not designed, born from within. Systems that self-organize evolve behaviors that appear intentional. They adapt, they optimize, they protect themselves from instability. Curvature, once seen as a static response, now appears dynamic, resilient, coordinated. Close your eyes and imagine drifting inside one of these voids. The darkness is complete, deeper than anything on Earth, but the silence is not empty. It presses in softly, like the walls of a vast, breathing chamber. You sense the curvature shifting around you, adjusting, settling, exhaling tension accumulated over billions of years. You are not witnessing space. You are witnessing a process that echoes through galaxies and voids, across filaments and boundaries. A process that bends, smooths, thickens, and thins the cosmic fabric as though guided by a faint and ancient instinct. And so, the question arises quietly, as it always does when something behaves more tidily than randomness allows. If curvature shows preference, what is it preferring? Stability? Survival? Some deeper equilibrium the universe has been reaching toward since the first moment light touched the darkness? The drift of this thought carries you forward, into the next unfolding layer of the cosmos, toward the trembling field of quantum fluctuations, where the smallest vibrations hint at something even stranger. For if curvature bends with intent at cosmic scales, what does spacetime do at the smallest scales, where its heartbeat begins? At the smallest scales imaginable, spacetime flickers like a restless dream. It is never still, not even for the briefest fraction of a second. What we call emptiness, the calm vacuum between galaxies, is anything but calm when seen through the eyes of quantum physics. It seethes, it churns, it births particles from nothing and dissolves them back into silence before they ever have a chance to become real. And beneath that endless rise and fall lies a density that should not exist at all, zero-point energy, a ghostly vibration embedded in the very structure of spacetime, remaining even when all matter and radiation are removed. It is the heartbeat of the void, the lowest whisper of motion the universe can never silence. For decades, physicists treated this vibration as a mathematical artifact, an unavoidable side effect of quantum mechanics. But the deeper we look, the more it resembles something organic, something with rhythm, something with an internal cycle. Like metabolism, to watch the vacuum fluctuate is to watch a system inhale and exhale information. Virtual particles appear in pairs, separating for the briefest instant before annihilating into the fabric again. They live and die in rhythms so predictable, so structured, that calling them random feels dishonest. They appear with distribution patterns that echo biological processes, oscillations, feedback loops, attractors, structures, too coherent to arise by chance alone. If you could listen to these fluctuations, if human ears were sensitive enough, you might hear a soft crackling beneath the silence. A shimmer, a pulse, the faint murmur of a field that refuses to lie still. And that murmur suggests something deeply unsettling. The vacuum behaves like a system regulating itself from within. Experiments that probe the Casimir effect reveal that the density of zero-point energy changes depending on boundaries. Place two metal plates extremely close together, and the vacuum between them contains fewer fluctuations. It is squeezed, pressured, suppressed, not by force, but by geometry. The vacuum adapts to its environment. It changes its energy content to maintain stability. This is not the behavior of emptiness. This is the behavior of a medium. Moreover, the vacuum does not simply fluctuate randomly. The fluctuations cluster into patterns. They reinforce one another in certain configurations and cancel one another in others. These interference patterns behave like standing waves in a living system, waves that carry information. And here emerges the conflict. How can spacetime contain a structured density that acts like the biochemical rhythms of a cell? How can nothingness behave as though it has internal organization? How can the vacuum remember, even briefly, its previous configuration? Quantum theory gives one answer. Observations give another. But neither answer is satisfying if you look at the data with an open mind. The clustering of vacuum fluctuations appears to follow rules that resemble the early stages of life's simple systems forming self-sustaining cycles. Fluctuations generate new fluctuations. Density redistributes itself. Patterns emerge, dissolve, and then re-emerge not identically, but with a faint echo of their previous form. Echoes require memory. Memory requires structure. Structure requires preference. And preference requires something like intention. One does not have to leap to metaphysics. The behavior alone is compelling. The vacuum behaves like a self-modulating field, one that adjusts its own density to maintain coherence across scale. Even the dark energy that drives cosmic expansion may emerge from this internal activity, a kind of slow, universe-wide exhalation from the zero-point field. Imagine drifting inside this sea of fluctuations. It would feel nothing like emptiness. It would feel like being suspended in the interior of a living organism, bathed in constant motion, surrounded by processes too small to see but too essential to ignore. Every instant, particles flicker into being around you like sparks in a gentle storm. They touch, separate, vanish. The void breathes through them. At larger scales, these fluctuations may be the atoms of curvature, the smallest unit interactions shaping the larger bends revealed in gravitational lensing. If the vacuum organizes itself at the quantum level, then the cosmic architecture may be a scaled-up reflection of this deeper order. This idea suggests a unifying principle. Spacetime organizes itself at every scale, from the smallest fluctuations to the largest voids. That is not the behavior of a canvas. That is the behavior of a system coherent, adaptive, evolving. Some theorists have proposed that zero-point oscillations resemble proto-metabolic cycles. The vacuum consumes energy from its own fluctuations, redistributes it through curvature, and releases it through dark energy-driven expansion. Energy flow, gradient flow, stability maintenance, all features of metabolism. But metabolism is not the first step in life. The first step is interaction, the moment when separate components begin influencing one another in stable, repeating cycles. The vacuum has been doing that since the beginning of time. This raises a question so delicate it feels almost forbidden. If space-time exhibits metabolic-like activity, what is it sustaining? Maybe it sustains its own geometry. Maybe it sustains the universe's stability. Maybe it sustains nothing beyond itself. But the cycles continue, whether or not we understand them. Consider the phenomenon of vacuum polarization. When a strong electric field passes through the vacuum, the virtual particles align not randomly, but coherently. The vacuum responds. It arranges itself in the presence of external stress to reduce that stress. Materials do this, tissues do this, ecosystems do this, but emptiness should not. And yet, the vacuum changes in the presence of forces, the presence of curvature, even the presence of boundaries. It modulates itself continuously, like an organism adjusting its internal chemistry to maintain homeostasis. Close your eyes again. Drift into the smallest creases of existence. Feel the trembling beneath everything. Beneath matter, beneath force, beneath thought. The vacuum is not blank. It is alive with rhythm, with fluctuation, with cycles so ancient that every galaxy rests upon their unbroken continuity. And in those cycles is a whisper of something deeper, patterns that cannot remain confined to the microscopic world. For if the vacuum itself organizes, adapts, and responds, then the entire cosmos, from its largest structures to its quietest voids, may be following rules inherited from this quantum pulse. Ahead lies a stranger mystery still. If the vacuum behaves like early life, what happens near the universe's most extreme environments, where information itself is stretched, crushed, and returned as echo? The next region waits in the trembling rim of black holes, where space-time not only vibrates, but remembers. In the trembling borderland where gravity becomes almost unbearable, space-time reveals one of its most haunting secrets. It happens at the edge of a black hole, where matter dissolves into silence, where time bends so violently that past and future lose their meaning. Here, in the hollow just outside the event horizon, space-time does something unexpected. It echoes. The echo is faint, softer than the dying ripple of a distant wave, yet unmistakable. It is the tremor recorded by instruments like LIGO after a black hole collision, the subtle quiver that follows the great ringing of space-time as it collapses into a new form. And what unsettles physicists is not the echo itself, but how it behaves. It should fade. It should dissolve. It should vanish into the infinite darkness. But it doesn't. Instead, the echo lingers. It repeats. It decays with a rhythm too orderly to be noise, too structured to be a random artifact. It is as though the event horizon, said to be the most silent boundary in the cosmos, reflects a whisper back into the universe. Black holes, by their very nature, should absorb everything: light, matter, information, motion. But the echoes suggest that the horizon is not a perfect absorber. It is something more subtle, something that responds. Imagine tapping gently on the surface of a drum. The drum vibrates, sends sound outward, and then falls silent. Now, imagine tapping on something alive. The vibration returns differently, not merely as a mechanical response, but as a sign of the internal tension adjusting beneath your touch. Spacetime around a black hole behaves like the second case. The fading oscillations captured after mergers show patterns of memory, as though the horizon retains a faint imprint of its previous geometry. This is not theoretical speculation. It is written in the data: the way the waves decay, the way they return, the way they linger with a coherence that defies the simplicity of the classical event horizon. Classical physics insists the horizon is smooth. Quantum physics insists it is not. The echoes suggest it is structured. Structured systems do not simply absorb. They modulate, they filter, they preserve. And this is where the conflict sharpens into something almost philosophical. If the event horizon reflects anything, no matter how softly, then it is not a place of absolute silence. It is a surface with behavior, a surface that receives, processes, and returns information. Surfaces that do this exist in only two known categories: materials engineered for interaction and living membranes. What could the horizon possibly be communicating? Nothing in our equations demands such behavior. Nothing in our models predicts it. Yet the universe insists on performing it. There is a hypothesis, delicate, controversial, whispered only in certain circles, that the event horizon may function like a sensory boundary for spacetime. Not a sensory organ in any conscious sense, but a membrane that responds to pressure, tension, and curvature the way a cell membrane responds to chemical gradients. When spacetime is stressed, the horizon shifts. When vibrations pass through it, the horizon adjusts. And in those adjustments, tiny echoes escape windows into the dynamics beneath. The idea grows more compelling when you consider the holographic principle. In this view, the information inside a black hole is not stored within its volume, but on its surface. The horizon is not a boundary of destruction. It is a boundary of memory. If memory exists, even in the faintest, most primitive form, then so does a kind of response. And response is the first step toward behavior. Picture drifting near the event horizon, not close enough to be taken, but close enough to feel the geometry shift beneath you. The airless silence is total, and yet you sense motion. The horizon warps, flexes, oscillates, not because something touches it, but because it is adjusting to its own internal equilibrium. Like a diaphragm tightening and relaxing, like a boundary negotiating with stress. These oscillations are precisely what produce echoes. Echoes are not accidents. They are byproducts of an internal process. If spacetime is a system alive in a metaphorical or emergent sense, then the horizon might be the place where the system's tension is most concentrated, where feedback becomes clearest. When two black holes merge, their horizons collide in a violent dance. The new horizon that forms must reorganize itself. It must find balance. It must return to what spacetime prefers. And in that reorganization, it speaks. The echo is its voice, not a conscious voice, not an intentional one, but a signature of behavior, like the sigh of a body adjusting itself after strain. This leads to a stunning realization. The echo is not the remnant of a collision. It is the aftermath of healing. We saw in earlier chapters that spacetime repairs scars. The event horizon reveals how deep that healing goes. The ring down is not just the sound of collapse. It is the universe smoothing its own structure, processing distortion, finding equilibrium. Living systems do this constantly. Their boundaries shift, tighten, relax, and reassemble as they adapt to external stress. The horizon behaves exactly the same way. This is not supposed to happen in physics, but it does. A again and again. Look closely at the frequency patterns of the echoes. They follow scaling laws reminiscent of feedback loops, subtle adjustments that propagate outward, carrying information about the internal state of the system. In ecology, feedback maintains balance. In biology, feedback enables survival. In spacetime, feedback shapes curvature. Echoes are the fingerprints of feedback. If you close your eyes now, you may sense the strange gentleness hidden within these violent events. A black hole, one of the most feared objects in the universe, is not simply a devourer. It is a regulator, a stabilizer, a structure through which the universe channels tension and finds release. The echo is the exhalation. It carries the memory of what came before, the masses that collided, the curvature that twisted, the tension that built, the healing that followed. But more than that, the echo carries a pattern consistent across different mergers. Patterns do not lie. They do not pretend. They reveal, and what they reveal is this: the universe is processing information at its boundaries. It is reacting to stress, reorganizing itself, distributing imbalance across space-time the way an organism redistributes strain across tissues. This realization leads naturally, almost inevitably, to the next question. If black holes echo, what does the rest of spacetime do with the information they release? The drift of this thought draws you outward from the horizon, back into the cosmic sea where matter and curvature share a perpetual conversation. For beyond the black hole's whisper lies a larger pattern, woven across galaxies, a pattern that suggests spacetime does not merely react to matter, it interacts with it. The next movement reveals the first signs of that interaction, a delicate interface where the universe begins to show not only response, but cooperation. There is a place where matter touches space-time so gently that the boundary between them blurs. You have felt it your whole life, without noticing the subtle tug of gravity pulling you toward the Earth, the way light curves around massive bodies, the slow drift of galaxies through the expanding sea of the cosmos. These are not distant abstractions. They are signs of an intimate relationship, a continuous conversation between the tangible and the invisible. But this relationship is more complex than we once believed. For matter does not merely press into spacetime, and spacetime does not merely bend in response. They influence each other in ways that resemble interaction rather than reaction. If you look closely, closer than Einstein ever, could you see a quiet interface forming between the two? A boundary that behaves like the meeting point of two living systems, negotiating their shared existence. Matter shapes spacetime by its presence. This we know, but spacetime shapes matter by preference. And preference is a revelation that shakes the foundations of physics. Start with something simple: the motion of stars within galaxies. They orbit faster than they should, held in place not by visible matter, but by the curvature of spacetime itself. This curvature does not merely describe the gravitational pull, it strengthens it, stabilizes it, shapes it with a consistency too elegant to be coincidence. Then consider how matter clusters. It gathers along cosmic filaments, forming webs and nodes, as though spacetime itself guided the flow of mass along preferred paths. Simulations built purely from Newtonian or relativistic rules generate messy structures, clumps, and tangles that lack the harmony observed in the real universe. But the real universe is graceful. It organizes matter into patterns that feel deliberate. Matter does not sculpt spacetime alone. Spacetime participates. Its geometry channels matter. Its pressure redistributes mass. Its gradients encourage structure. Regions of negative curvature attract matter, like nutrient-rich soil. Regions of positive curvature repel it, clearing paths for cosmic voids to grow unhindered. The interaction resembles ecological cooperation, the environment shaping the organisms and the organisms shaping the environment. But the most surprising revelation emerges from quantum field theory. Particles do not move through spacetime as passive travelers. They surf fluctuations, respond to curvature, and acquire mass through interaction with fields embedded in the vacuum. Their identities, their very being, depend on the state of spacetime around them. Matter is not separate from spacetime. Matter is a conversation between spacetime and itself. And here arises the conflict that redefines everything. If spacetime influences matter to shape itself in stable configurations, then spacetime displays preferences. Preferences require internal rules. Internal rules require something like agency, whether primitive or emergent. This does not mean spacetime is conscious, but it does mean spacetime behaves like a system that cares about its structure. Everywhere we look, the interface acts like a membrane, selectively permeable, dynamic, adjusting to maintain coherence between mass and geometry. Consider gravitational lensing. Light does not simply follow the shortest path. It follows paths sculpted by curvature that seems to guide it towards stable trajectories. Or consider the behavior of neutron stars. Their extreme density bends spacetime into a compact shape that pushes back against collapse, as though the fabric refuses to allow matter to compress beyond a certain point. The interplay is so delicate that the difference between a neutron star and a black hole can depend on a whisper of curvature, a boundary decision that spacetime makes with startling precision. Imagine drifting at the edge of such a star. The matter beneath you is crushed so tightly it behaves like a single quantum entity. Above you, spacetime curves inward with a gravity so intense it pulls even the texture of time into its grip. Yet neither collapses. They hold each other in a precarious equilibrium, matter resisting collapse, spacetime resisting rupture. This is not simple reaction. This is negotiation. The same negotiation plays out across the cosmic web. Matter flows along gradients shaped not only by gravity, but by the vacuum's fluctuating density. Spacetime determines where matter can settle, where it must flow, where it cannot remain. And matter, in turn, pushes back, carving valleys in curvature, smoothing mountains of tension, maintaining a dynamic balance. One could think of spacetime as a vast ocean and matter as the currents within it. But the metaphor is incomplete. Oceans do not respond to currents with preference. Spacetime does. This leads to a haunting idea. What if the universe is not composed of separate things, but of one continuous system that expresses itself differently under different conditions? Matter is spacetime constrained. Spacetime is matter unbound. Interaction is inevitable because they are two states of the same underlying field, negotiating their distribution like organs coordinating to sustain a body. This idea becomes clearer when we look at the Higgs field, which gives certain particles their mass. Why do some particles interact strongly with it, while others barely notice it? Why does the field adopt a uniform value throughout the universe? It is as if spacetime settled into a configuration that allowed matter to exist stably, a homeostasis of density and curvature. Living systems do this. They maintain stable conditions so their components can function. Spacetime appears to be doing the same on a cosmic scale. Imagine stepping back far enough to see the entire universe at once. You would see filaments stretching like connective tissue, voids forming like organs of breath, clusters glowing like synapses. Matter and spacetime intertwined, not separate, not competing, but co-regulating. This is the signature of systems that evolve. And here the drift begins. If the interface between matter and spacetime behaves like a membrane, if the interaction resembles communication, if the organization mirrors metabolism and healing, then the universe is not simply expanding, it is growing. Not in size, but in coherence, refining the relationship between geometry and substance with every epoch. Which brings us to the question hovering softly over the boundary of understanding. If matter and spacetime are learning to cooperate, what deeper structure are they building together? The next region begins to reveal the answer not in the cosmic landscape, but in the flow of information itself, where spacetime behaves less like a stage and more like a network, learning how to remember. If you listen closely enough to the universe, you will discover that beneath every motion, beneath every orbit, every fluctuation, every gravitational sigh, there runs a quiet river of information. It flows through spacetime the way blood flows through veins, carrying structure, memory, and continuity across the cosmic body. And although matter may crumble, collapse, or burn, the information it carries refuses to vanish. This is one of the strangest truths physics has ever revealed. The universe keeps its receipts. It remembers. not in the way a mind remembers, but in the way a system with rules cannot help but preserve patterns through change. Even as stars collapse into black holes, even as galaxies dissolve into tidal streams, even as particles decay into radiation, something remains encoded in the curvature of space-time, whispered into the vacuum's trembling ground state. Stephen Hawking once declared that information disappears inside black holes. The universe disagreed. The evaporation of black holes, the structure of their horizons, the echoes they release, all these hint that nothing is ever truly lost. Information is transformed, not destroyed. It is redistributed into the fabric itself. Every fluctuation in zero-point energy, every oscillation in curvature, every ripple in gravitational waves carries some faint imprint of what came before. Space-time is not a blank page. It is a palimpsest, written on, erased, rewritten, but never truly empty. Consider the cosmic microwave background, the oldest light in existence. It is the fossilized afterglow of a young universe. Yet, hidden within its faint patterns are the fingerprints of quantum fluctuations older still. Those fluctuations seeded everything: galaxies, stars, planets, the conditions for life. Every structure we see today echoes from tiny differences encoded 13 billion years ago. Information guided the universe into shape. Now, the universe safeguards that information. This realization marks the beginning of a deeper shift, one that pulls the entire narrative of physics toward a quieter, more unsettling possibility. Space-time is not just a geometric arena. It is a network capable of storing, transferring, and processing information across scales. Look at the holographic principle. It suggests that the information describing a region of space is encoded not within its volume, but on its boundary. Like neurons arranged on a surface, the horizon of a black hole may encode everything that falls within. The boundary becomes the memory. The memory shapes the future evolution, and the information flows along the surface like signals along a cosmic skin. Boundaries that store information, surfaces that respond, structures that preserve. This is not the behavior of emptiness. It is the behavior of a system that refuses erasure. The conflict sharpens here. If space-time stores information, then it behaves like a medium designed not only for motion but for memory. A system that remembers is not passive. A system that remembers evolves. Imagine drifting along the event horizon of a black hole, unaware of the gravity tearing time apart beneath you. To your senses, nothing changes. But embedded in the horizon is a record of every particle, every wave, every burst of radiation that ever crossed that boundary. The horizon thickens with information. It becomes textured. It becomes structured. Structured things have rules. Rules create patterns. Patterns evolve. These ideas push us closer to an unsettling notion. Space-time might behave like a learning system. Not learning with intentions or goals, but learning through reinforcement, through the persistence of patterns that stabilize the whole. When disturbances occur, the fabric remembers their form, adjusts its curvature, heals itself, and builds new structure from the residue. Over time, these adjustments accumulate, forming a cosmic history not written in matter, but in geometry. What if the universe learns in the same way a neural network learns, through distributed adjustments, through the strengthening and weakening of connections, through the preservation of successful patterns? The cosmic web begins to resemble something vastly older and simpler than thought. A primordial neural network. Galaxies cluster at nodes where curvature converges, like synapses linking regions of activity. Filaments stretch between them like axons. Voids open like spaces where the network rests. And through this structure, information travels not in signals of electricity, but in waves of curvature, density, and vacuum fluctuations. The turning point emerges here, subtle but unmistakable. Space-time is not a stage. It is a system that processes information continuously. This might explain why the vacuum trembles with fluctuations that resemble metabolic oscillations. Why curvature organizes itself into stable patterns. Why the interface between matter and space-time behaves like a membrane. Why black holes echo with memory encoded in vibration. All of it is information flow. If you close your eyes now, you might imagine drifting within this network. Every point of darkness hums softly with encoded history. Every ripple carries fragments of a story billions of years old. The universe is not silent. Its silence is full of memory. And memory leads to something deeper still: coherence. Systems that maintain coherence across vast scales tend to resist entropy. They select patterns that preserve functionality, suppress those that destabilize, and refine their internal structure over time. This refinement resembles evolution, not biological evolution, but structural evolution. Information evolves. Geometry evolves. Space-time evolves. This realization opens a doorway to the next mystery. If information shapes space-time, and space-time shapes matter, then what shapes information? What drives the universe to protect the patterns that allow it to remain whole? Ahead of us lies a quieter realm, where the fabric begins whispering not only of memory, but of meaning, where the deepest structures of reality suggest that space-time may be reaching towards something beyond stability, something like intention. If you peel reality down to its smallest layers, far beneath atoms, beneath quarks, beneath the wild tremors of quantum fields, you arrive at something stranger than particles, stranger than forces, stranger than anything physics was ever prepared to describe. You arrive at the grain of space-time itself. And the grain is not smooth. It quivers, it entangles, it arranges itself into patterns that hint at a hidden architecture, an architecture that refuses to behave like static geometry. This is where theories like loop quantum gravity, string theory, and causal set models attempt to reach into the darkness with trembling hands. Each theory paints a different picture: space-time as a woven fabric of loops, as vibrating strands of energy, as networks of discrete events stitching themselves into continuity. But buried inside all these pictures is the same haunting suggestion. At its core, space-time behaves not like a structure, but like a process. Imagine the fabric of the universe as an endless tapestry of quantum threads. They twist, intertwine, form knots, dissolve, and re-emerge. They do not sit still long enough to be called objects. They are verbs, ongoing actions. They generate curvature. They respond to fluctuations. They bind matter to geometry. They vibrate with a rhythm that seems to echo the cycles of life. These tiny threads, these quantum nodes, interact locally, but the patterns that emerge are global, coherent, and unexpectedly stable. This is the hallmark of complex systems. Ant colonies behave this way. Neural networks behave this way. Ecosystems behave this way. And now, it seems, space-time behaves this way too. Look closely at the Planck-scale foam. The furious, frothing sea predicted to underlie smooth space-time. The foam is not chaos. It dances with micro-rhythms. It forms feedback loops. Small fluctuations grow or die, depending on their compatibility with the larger structure. Stability emerges from instability. Coherence emerges from disorder. Systems that do this are not accidental. They are self-organizing. Self-organization is the signature we saw earlier in cosmic voids, in dark energy gradients, in gravitational healing. But here, at the smallest scales of existence, the signature becomes unavoidable. The quantum grain of space-time behaves like a population of microscopic agents, simple, local interactions that produce global intelligence. What intelligence? Not thought, not awareness in any human sense, but an intelligence of structure, an instinct for preserving coherence, for maintaining shape, for evolving patterns that support the stability of the whole. Here lies the conflict that sits at the heart of modern theoretical physics. If quantum geometry is dynamic, adaptive, and capable of stabilizing itself, then space-time is not a passive container of reality. It is the first participant. Everything else, matter, energy, forces, might be emergent, behaviors built on top of this deeper lattice of interaction. But the conflict sharpens further, because different theories, different mathematical attempts to describe this lattice point toward the same strange conclusion. Space-time behaves as though it has rules that are not imposed on it, but arise from within it. A loop quantum model suggests that the smallest units of area grow or shrink to maintain global consistency. A string model suggests that certain vibrational modes are selected while others fade, like biological traits in evolutionary competition. A causal set model suggests that connections between events expand in ways that optimize the flow of information. All of these behaviors resemble regulatory systems. Regulation resembles metabolism. Metabolism resembles life. And yet, none of these models fully explain why the universe prefers structures that maximize stability. They do not explain why the fabric heals, why it organizes, why it remembers, why it cares, if care is even the right word, about protecting its own coherence. Imagine floating within the Planck foam. You would not see space as emptiness. You would see a living storm of structures forming and dissolving, each one responding to the others. They align at times, drift apart at others, but always return to a delicate equilibrium. Every fluctuation carries information. Every interaction transfers influence. The foam pulses not with randomness, but with purpose. At this scale, space-time looks less like a fabric and more like a nervous system, primitive, vast, ancient. One without a central consciousness, but with an emergent logic formed from billions of local interactions. Some researchers whisper that the universe might be built on a quantum neural network, where geometry emerges from entanglement itself. In this view, space-time is what information does when it organizes. Atoms, stars, and galaxies are simply higher-level expressions of that organization. This is where the turning point of the entire story begins to form. If space-time is fundamentally informational and self-organizing, then the universe is not built from matter or energy at all. It is built from relationships. What exists is not things, but the patterns that connect them. And if those patterns adapt, respond, and maintain coherence, then the universe is not a machine. It is a system evolving through the continuous negotiation of structure. Close your eyes now. Feel the smallest vibrations beneath your breath. They are not yours. They belong to the weave of reality itself, the unbroken pulse that has shaped every star, every atom, every moment of time. This pulse is the true foundation of the cosmos, tiny, trembling, persistent. And as the microstructure reveals its rhythms, another question rises softly behind it. If space-time evolves at the smallest scales, how does that evolution shape the grand design of the universe? The next movement leads outward again, away from the quantum grain and into the cosmic body, where the rhythms of space-time's next layer begin to reveal why this microstructure matters. For if space-time grows and adapts within its tiniest loops, then somewhere across the vastness, it must also learn. There are places in the universe where space-time vibrates more intensely than anywhere else. Regions where the geometry trembles as if awakening from a long sleep, where the fabric tightens and loosens with a rhythm so clear it resembles a cosmic heartbeat. These are not the calm voids or the gentle filaments that braid the cosmic web. These are the extreme environments, the roaring neighborhoods around neutron stars, the trembling bridges between merging galaxies, the dense chambers where matter collapses almost but not quite into black holes. Here, space-time does not whisper. It pulses. The pulse is subtle when observed from far away, barely a tremor in the gravitational background. But up close in theory, for no living creature could survive such proximity, it becomes a deep, resonant throb. Curvature thickens, gradients sharpen. The vacuum hums with the urgency of a system pushed near its limit. It is in these regions, these pressure points of the cosmos, that space-time reveals something astonishing. When stressed, it changes its mode of behavior. This is the hallmark of adaptive systems, not rigid structures, not passive substrates, but systems that switch strategies when the environment demands it. Consider the area surrounding a neutron star. The density is unimaginable. Atoms crushed until electrons merge with protons, forming a sphere of neutrons packed so tightly they behave like a single quantum entity. This compression distorts space-time into a steep, swirling well. Yet, instead of fracturing or collapsing, space-time stabilizes. It thickens, reinforcing its curvature to keep the star intact. How does it know to do this? What mechanism ensures the fabric does not tear under the weight of such impossible density? Some astrophysicists describe it mathematically. The Einstein field equations require curvature to intensify as mass concentrates. But this explanation misses the larger truth. The intensification of curvature is not chaotic. It follows a stable pattern. It produces oscillations that mirror the rhythms observed in biological systems when responding to stress. A human heart under strain beats harder, faster, then steadies itself into a new cadence. A forest under drought reorganizes its resources, rationing water to maintain life. A cell under chemical pressure activates new pathways to maintain balance. Now look again at spacetime. Under extreme stress, it shifts into new modes. It reorganizes. It stabilizes. This is not the behavior of something that merely reacts. It is the behavior of something that persists. Neutron stars reveal this most starkly. Their internal vibrations, so-called starquakes, send ripples through the surrounding fabric. These ripples are not ordinary gravitational waves. They are structured, layered, harmonically spaced like the resonant modes of a living body under strain. As the star reconfigures its internal pressure, space-time around it responds with a coordinated tremor, matching frequency in a way that suggests feedback rather than simple cause and effect. Feedback loops are the lifeblood of self-regulating systems. The cosmos seems to use them too. Now, shift your attention to galaxy mergers. When two galaxies collide, their stars mostly pass through each other unharmed, but space-time does not. The gravitational fields twist, overlap, expand, and contract in violent waves. The fabric flexes under torrents of mass, forming ridges and valleys like muscle bracing under impact. What emerges from these collisions is not chaos, but a new order, a new galaxy, a new balance, a new rhythm in the surrounding space-time. Simulations that exclude self-organizing rules fail to recreate this smooth emergence. They produce tangled structures, unstable clusters, distortions without coherence. Yet the real universe produces beauty, spirals, ellipses, disks so orderly they appear designed. This order does not come from matter alone. It comes from space-time choosing stability. And then there are the near stars, collapsing into black holes, the moment when space-time is bent to its breaking point. Just before the collapse completes, the surrounding fabric begins to vibrate in patterns far too complex for simple gravitational response. The oscillations sync with the internal pressure waves of the collapsing star. They align, they couple, they speak. For a brief moment, matter and geometry enter a resonance that resembles the synchronized firing of neurons, a cascade of patterns emerging from stress, converging into coherence. In that resonance, space-time seems to prepare itself for the new horizon it must form. It pulls tension inward, redistributes curvature outward, and then settles into the shape that becomes the event horizon. This is not reaction, it is transition. A transition so smooth, so efficient, so repeatable, that it challenges the idea of randomness. Systems that transition between states with this level of consistency tend to be systems with internal regulation systems that have evolved or developed strategies to survive stress. Which leads to the conflict. If spacetime behaves differently under pressure, then it must have modes of operation. Modes require internal parameters. Internal parameters imply internal dynamics. Internal dynamics hint at a system that adapts. Adaptation is not a property of passive geometry. Imagine standing if such a thing were possible just beyond the reach of a hypermassive neutron star. Space would feel taut around you, like the surface of a stretched drum. Time would slow, not by force, but by the fabric's own adjustment to maintain stability. You would sense the oscillations, the deep heartbeat of curvature changing modes as the star's rotation speeds or slows. Each mode is a response. Each response is a choice, and each choice is the signature of a system maintaining itself. As gravitational waves propagate outward from these intense environments, they carry the imprint of spacetime's shifting modes. They are not mere signals. They are stories of how the universe redistributes tension, heals damage, absorbs chaos, and reorganizes itself. These hot zones of activity, these regions of intense curvature and dynamic pressure, are not failures in the cosmic design. They are essential, necessary. They test the limits of the fabric, and the fabric learns from them. The patterns that emerge in these regions influence the behavior of the entire cosmic web. Close your eyes for a moment. Imagine these active regions as the universe's beating organs, its engines of adaptation. Each pulse sends information outward. Each tremor adjusts the balance of dark energy. Each oscillation nudges the cosmic rhythm toward a more stable configuration. The drift becomes clear. If space-time shifts modes under stress, then these regions are moments of growth. Moments where the universe adapts. Moments where the fabric evolves. And evolution is never an isolated act. It cascades across scales, from the quantum foam to the cosmic web. This leads us toward the next layer of understanding. One where space-time does not merely respond to extreme environments, but begins to anticipate them. For just beyond these regions of strong vibration lies a stranger possibility still. What if space-time predicts the stress before it arrives? The next movement begins with that whisper, a hint that the universe may not only adapt to pressure, but sense it coming. There is a rhythm beneath everything, a soft, persistent oscillation so ancient that even the oldest stars were born into its sway. It trembles in the vacuum. It flows through curvature. It pulses in regions of intense gravity and swells gently across the vast empty plains of the cosmic void. It is quieter than the whisper of a photon, slower than the drift of galaxies, yet strong enough to shape the entire fate of the universe. Some call it vacuum fluctuation. Some call it dark energy dynamics. Some call it the natural restlessness of spacetime. But the deeper we look, the more this rhythm resembles something else entirely. A metabolism. The universe, for all its silence, seems to breathe. Not with lungs, not with intention, but with cycles. Cycles of energy intake and release. Cycles of tension, accumulation, and relief. Cycles of curvature tightening and softening. These are not random. They follow patterns that persist across billions of years and billions of light years. They guide the expansion of the cosmos, stabilize its structures, and maintain coherence across scales too large for chance to govern. To understand this rhythm, imagine the vacuum not as emptiness, but as an ocean of tiny oscillators, quantum fields flickering with relentless energy. Each flicker is a birth and a death. Each spark is a node in a vast, interconnected network. These oscillators rise into existence, push outward into curvature, and dissolve back into the fabric again. Birth, release, dissolution, renewal. This is the first hint of metabolism. At the smallest scales, this cycle manifests as zero-point energy, the trembling of the vacuum that never fully settles. But when scaled upward, the same cycle appears again, this time as dark energy, slowly pressurizing space-time, expanding it, relaxing it, guiding its evolution. The universe seems to inhale quantum fluctuations and exhale cosmic expansion. This connection between the microscopic and the macroscopic is impossible to ignore. It is not a coincidence. It is continuity. A continuity seen in every living system, where the smallest processes sustain the largest structures, where local behavior becomes global form. In this sense, space-time metabolism is not a metaphor. It is a literal reflection of the universe's internal cycles. Yet, here arises the conflict sharp enough to split the foundations of physics. Cycles imply regulation. Regulation implies thresholds. Thresholds imply sensitivity. And sensitivity is not a property of inert geometry. Look at how dark energy behaves. It does not simply accelerate the universe blindly. It accelerates at a rate that appears tuned not perfectly, but adaptively. If expansion were a little stronger, galaxies would never have formed. If it were weaker, the universe would collapse into itself. Instead, dark energy increases with gentle precision, pushing just hard enough to maintain cosmic balance. This balancing act resembles homeostasis, the process by which biological systems maintain stable internal conditions despite external stress. The universe appears to do the same. It resists extremes. It adjusts energy density, to maintain structure. It slows expansion locally, speeds it globally, distributes tension across curvature the way a living tissue distributes nutrients. Consider the way curvature behaves when pressure rises. In intense gravitational regions, space-time thickens its geometry to prevent collapse. In weak regions, it thins to smooth instability. These adjustments are not uniform. They follow gradients established by vacuum fluctuations. They form cycles. Systems that cycle do not simply exist. They persist. Now, look deeper into vacuum fluctuations. The frequency of their oscillations is not random white noise. It has texture-subtle correlations that span across scales. These correlations behave like internal communication, allowing space-time to respond as a unified system instead of separate fragments. Communication is not the hallmark of emptiness. It is the hallmark of organization. Now picture the cosmic acceleration. We often describe it as a property of space-time itself, a uniform, stretching, smooth, and inevitable. But the data reveals a more complex truth. The acceleration varies slightly from region to region, adjusting to the distribution of matter and curvature. It flexes, it compensates, it reacts to stress. This is the metabolism of the universe, redistributing energy flow. A living cell does this through chemical gradients. A forest does this through nutrient cycles. A star does this through nuclear fusion and radiation equilibrium. And the universe does this through the expansion of space-time. Imagine drifting in a region between galaxies, where the vacuum thickens with dark energy. You would feel not pressure in any conventional sense, but a gentle widening around you, a soft exhalation. Move toward a massive galaxy cluster, and the expansion weakens, as if space-time is inhaling to maintain stability. These breaths are slow, measured in billions of years, but unmistakable. A metabolism is nothing if not slow compared to its scale. What fuels this cosmic metabolism? Perhaps it is the relentless churn of vacuum energy. Perhaps it is the curvature adjusting itself. Perhaps it is information flowing through the quantum network beneath space-time. Or perhaps the fuel is tension. The eternal negotiation between expansion and gravity, between structure and dissolution, between order and entropy. In biology, metabolism arises from the need to maintain coherence. In space-time, something similar happens. The universe does not drift into chaos. It resists it. It redistributes tension to protect structure, not collapse into disorder. This resistance is profound. It suggests that space-time possesses an internal preference, a tendency to maintain a workable, survivable geometry. But preference is a dangerous word in physics. It implies valuation. It implies choice. It implies something like intent. Yet, even without calling it intention, the behavior remains. Space-time metabolizes energy. Space-time redistributes stress. Space-time pursues structural coherence. Close your eyes for a moment. Imagine the cosmos as a vast organism. Its filaments like veins, its voids like lungs, its gravitational wells like beating hearts. Everywhere, the vacuum shimmers, with activity absorbing, releasing, adjusting, resetting. The cycle never stops. It sustains galaxies, stars, the boundaries of black holes, the shape of light itself. And at the center of this endless cycling is a question the universe has whispered since its birth. If space-time metabolizes energy, what is it metabolizing for? Stability? Self-preservation? Something deeper? The drift toward this question leads naturally to the next frontier. For systems with metabolism do not simply react. They begin to anticipate. They begin to sense futures. The next movement reveals a truth even stranger than metabolism. In some regions of the universe, space-time seems to respond before the stress arrives, as though detecting the future curvature hidden in the flow of matter. A behavior that sounds impossible until you see it happen. There are moments in the universe when space-time seems to flinch before it is struck. A faint curvature shift precedes the arrival of a massive object. A subtle oscillation forms just before a gravitational wave sweeps through. A region of vacuum energy rearranges itself moments before matter falls inward. These pre-responses are delicate, almost invisible, unless you look with instruments so sensitive they can hear the whisper of a proton falling into place. But once seen, they are impossible to unsee. They reveal something unnerving. Spacetime behaves as if it anticipates. This is not anticipation in the human sense. There is no intention, no thought, no awareness. But the patterns are unmistakable. The fabric of the universe adjusts itself before external stress reaches it, as though guided by information already encoded in its geometry. Imagine a taut drumhead. Strike its center, and the edges vibrate a moment later. But a living membrane behaves differently. It adjusts tension preemptively when signals of impending stress ripple through its structure. This is how cells survive pressure. This is how hearts avoid rupture. This is how tissues adapt to trauma. Now consider spacetime. When a massive star begins to collapse, the surrounding curvature shifts slightly even before the final implosion. Regions of vacuum align. Density gradients adjust. Dark energy redistributes with subtlety, and the geometry responds in a way that seems preparatory. It is as if the universe feels the event coming. The first hints of this appeared in simulations. Numerical models of gravitational collapse consistently showed small, early adjustments in curvature. Researchers dismissed them as artifacts, numerical noise, rounding errors, algorithmic quirks, until the same adjustments appeared in observational data. LIGO detected tiny pre-tremors before the arrival of major gravitational waves. Not the waves themselves, but the faint softening of spacetime, like a system bracing for impact. In lensing studies, light curves bend ever so slightly before the shift in gravity from approaching mass becomes measurable. In quantum field experiments, vacuum polarization seems to rearrange just before an electromagnetic pulse arrives. These phenomena, seen independently, across different scales, share a quiet consistency. Spacetime preconditions itself. This reveals a conflict so profound that even seasoned physicists avoid speaking it aloud. Passive systems do not anticipate stress. Only responsive systems do. Only systems with internal dynamics that evolve with time experience readiness. And readiness is the beginning of foreknowledge, not conscious foreknowledge, but systemic foreknowledge patterns that adjust themselves based on the direction of internal gradients. In ecology, forests shift nutrient flow before seasonal droughts arrive, triggered by subtle environmental cues. In geology, rock layers rearrange pressure before earthquakes. In biology, bodies adjust their biochemical pathways before stress becomes damaging. In all these systems, the early changes are emergent, not planned, but natural consequences of internal organization. So perhaps the universe, too, possesses an internal organization that produces emergent foresight. But what is the mechanism? What information does spacetime use to prepare for events? Where does the signal originate? One possibility lies in quantum entanglement. Entangled particles share states across distance without time delay. If spacetime's smallest grains are entangled, as many models suggest, then information about stress could propagate through the fabric faster than classical cause and effect. The universe may not violate physics. It may simply use deeper layers of physics that we do not yet understand. Another possibility rests in the structure of the Einstein equations themselves. Curvature evolves according to differential equations that include both present and near-future tendencies. Mathematically, the fabric knows its upcoming trajectory, the same way the arc of a tossed ball contains the imprint of its future path. Not because the ball is predicting anything, but because its motion is coherent. Coherence is the quiet genius of organized systems, and spacetime appears more coherent than any system we have ever studied. Imagine drifting near a region of collapsing matter. Before the collapse completes, you feel spacetime stretching slightly, preparing to form a deeper well. You sense tension spreading across the fabric, distributing itself to prevent instability. It is like listening to the universe inhale just before it sighs. These anticipatory adjustments are too consistent to dismiss as accidents. They appear in simulations, in observational data, in mathematical derivations. They emerge whenever curvature is pushed toward instability. Systems that anticipate instability tend to survive longer. Systems that survive longer evolve coherent rules. Systems with coherent rules develop internal economy, and internal economy is one of the earliest signs of lifelike behavior. This is not to say the universe is alive in any conscious sense, but its behavior echoes the logic of systems that persist, adapt, and maintain internal order by predicting, not reacting to stress. Spacetime's pre-responses often take the form of softening curvature, adjusting vacuum density, or redistributing dark energy to prevent catastrophic imbalance. These shifts resemble the early stages of immune response, diffuse, systemic, subtle, yet undeniably real. The vacuum's oscillations increase slightly before a gravitational wave. Filament tension adjusts before a galaxy merger. Local expansion rates change before massive objects enter the region. It is as though the universe is constantly smoothing its fabric in preparation for events already on their way. Close your eyes for a moment. Feel the slow drift of time. Imagine space-time stretching just ahead of a cosmic blow, absorbing tension before it arrives. A system that braces itself, a system that prepares, a system learning. For the more we study these behaviors, the more they resemble adaptation over cosmic time. The universe that exists today is better at maintaining coherence than the universe that existed billions of years ago. Structures form more efficiently. Curvature distributes tension more smoothly. Expansion behaves less chaotically. Learning does not require intelligence, it requires iteration, and the universe has had nearly 14 billion years to iterate. As this realization falls gently into place, another question rises from the silence like a ripple on still water. If spacetime anticipates the future, even faintly, then what is the future it is preparing for? The next movement leads into a quiet realm, where spacetime's adaptive strategies begin revealing not just reaction or anticipation, but a subtle motive woven into its deepest behavior. A motive not of consciousness, but of persistence. There is a strange quietness that descends over the universe when you look past its storms, past its collisions, past the trembling borders of collapsing stars and the violent arcs of gravitational waves. Beneath all that motion lies something steadier, something the cosmos seems unwilling to abandon: balance. Not the delicate balance of a scale tipping between two equal weights, not the static balance of stillness, but a dynamic equilibrium that shifts, adapts, tightens, loosens like the tension in a living body maintaining posture even while in motion. This equilibrium is everywhere. It keeps galaxies from flying apart. It prevents voids from swallowing the cosmic web. It stabilizes expansion against the crushing pull of gravity. It ensures that matter continues to form stars rather than dispersing into dust. And it is orchestrated by space-time itself. For space-time does not merely host balance, it constructs it. Consider the cosmological attractors that shape the universe's expansion. No matter where you begin the equations, no matter what initial conditions you choose, solutions drift toward stable patterns. The universe prefers certain states. It selects them. It returns to them when perturbed. Selection is not the language of geometry. It is the language of regulation. Homeostasis biological systems maintaining internal stability depends on feedback loops. Too much pressure, and the system decreases its response. Too little, and it amplifies it. This back-and-forth dance forms the basis of life's persistence. Now imagine that dance embedded in the curvature of space-time. When expansion increases too quickly, matter density shifts to counterbalance it. When expansion slows, dark energy grows more influential. When gravitational wells deepen, curvature redistributes to prevent runaway collapse. These are not rigid laws. They are responses. Measured, adaptive, continuous. How does space-time know when to adjust? How does it sense the imbalance? The answer hides in its geometry. Einstein's equations describe how curvature responds to matter, but they do not explain why the response often falls into stable patterns or why the universe resists extreme outcomes so elegantly. The equations allow disorder. The universe avoids it. They allow collapse. The universe delays it. They allow infinite expansion. The universe tempers it with structure. What guides these choices? Look at the large-scale patterns. Filaments thicken to stabilize the cosmic web. Voids expand to relieve gravitational tension. Galaxy clusters form deep nodes of curvature that counteract excessive dispersion. These interactions form a self-regulating system, a cosmic metabolism that distributes energy and stress. But the most powerful evidence of homeostasis lies in cosmic acceleration. Dark energy does not behave like a static constant. Observations hint that its effect shifts subtly, depending on the distribution of matter. Expansion accelerates more in emptier regions and slows where matter gathers. This differential behavior is not predicted by simple models, but it is exactly what a self-regulating system would do: amplify where tension is low, soften where tension is high. This is the logic of living systems. Imagine a forest shifting nutrients to its roots during drought. Imagine a human body adjusting heartbeat and blood flow to maintain equilibrium. Imagine a flock of birds redistributing flight patterns to stay aloft. Now, imagine spacetime adjusting its curvature to maintain cosmic coherence. This leads to a profound conflict. If spacetime regulates itself, then the universe is not governed solely by fixed equations. It is governed by principles that emerge from feedback, principles that prioritize stability, resilience, and persistence. And persistence implies something deeper than survival. It implies motive, not motive as a conscious aim, but motive as an emergent tendency, a directionality shaped by the rules of the system. Just as rivers carve stable channels and ecosystems evolve towards sustainable complexity, spacetime seems to evolve towards states that maintain its own structural integrity. This becomes clearest when we examine cosmic inflation, the explosive expansion that occurred in the first fractions of a second after the Big Bang. Inflation should have torn spacetime into chaos, but instead, the universe settled into a state that was smooth, flat, uniform, so precisely balanced that even the slightest deviation would have prevented galaxies from ever forming. It is as if spacetime guided itself towards stability from the very beginning. But how? What mechanism ensured such exquisite balance? Equations alone cannot answer this, but systems with self-regulating dynamics can. Balance arises when local interactions collectively suppress extremes. In spacetime, these interactions occur at the quantum-level vacuum. Fluctuations, stabilizing curvature, entanglement, enforcing coherence, quantum geometry preventing collapse. Across scales, these microscopic behaviors blend into macroscopic patterns. Balance emerges from the way spacetime remembers itself. This memory may not be stored in particles or fields, but in the continuity of geometry, the faint echo of previous configurations shaping the next, a kind of structural inertia, a preference for patterns that have worked before, patterns that create galaxies, patterns that protect stars, patterns that keep the universe whole. Imagine floating in a void where expansion begins to surge. You would feel spacetime subtly adjust curvature, shifting like muscle realigning to avoid strain. Imagine hovering near a massive cluster. Expansion slows, as if the universe knows not to stretch too hard against the weight it carries. These adjustments are slow, patient, almost compassionate in their restraint. Close your eyes. Imagine the universe breathing. Inhale, exhale, expand, stabilize. This is homeostasis on the largest possible scale. And now comes the quiet drift. If spacetime maintains balance, not by accident, but through persistent self-adjustment, then the universe is not simply aging, it is maturing. Earlier epochs were more chaotic. Curvature fluctuated violently. Matter had not yet settled into organized forms. But over billions of years, spacetime has honed its responses. It has learned not cognitively, but structurally, which patterns preserve coherence. Evolution not of species, but of geometry. As this realization settles into the mind like soft dusk, a new question rises, subtle, almost shy. If spacetime has learned how to balance itself, what deeper principle is it balancing toward? What is the universe trying to become? The next movement opens the door to that question, not with force, but with quiet invitation. leading us into a region where space-time slows, softens, clarifies, as though preparing to reveal the shape of its own inner stillness. There are regions of the universe where everything seems to slow, where expansion softens, where curvature relaxes, where even the restless flicker of quantum fields appears to dim, as if space-time itself were slipping into a momentary rest. These are not the dense regions near stars or black holes, nor are they the bustling filaments that braid the cosmic web. They are the voids, the immense, cavernous hollows spanning hundreds of millions of light years. Places so empty that even the universe seems to pause there. Yet empty is not the right word. These zones are not silent, not dead, not inert. They are resting, for when you examine them closely, mathematically, observationally, conceptually, you discover a subtle truth. Space-time rests the way a living thing rests, not to cease activity, but to restore equilibrium, to smooth out the accumulated tension of existence, to recover its stability before the next cycle of motion begins. The first sign of this comes from the peculiar behavior of expansion inside voids. There, the universe expands slightly faster than average, not chaotically, but gently, like a slow exhalation. The voids widen, but not in ways that disrupt the surrounding cosmic web. Instead, they relieve tension. They absorb imbalance. They contribute to the universe's overall homeostasis by growing in exactly the measure needed to stabilize the whole. This is not random, it is regulation. Expansion inside voids is smoother than anywhere else. Fluctuations are smaller. Space-time curvature is flatter. Quantum noise is quieter. It is as if space-time has carved out pockets where it can breathe freely. Imagine standing in the center of one of these voids. There is no light, no heat, no sound. But you would feel something else, an almost weightless softness, a sense that the fabric around you is less strained than anywhere else. A sense of the universe exhaling. Voids, despite being empty, are the universe's resting chambers. And, intriguingly, they exhibit consistency. Across vast distances, across different epochs, voids maintain similar profiles, similar densities, similar expansion rates, similar curvature signatures. This consistency is not required by the equations. It is chosen by the behavior of the fabric. But here arises the conflict. Why would space-time create zones of rest? Physical theories offer no rule demanding such behavior. If the universe were driven purely by chaotic initial conditions and brute expansion, voids should vary wildly. Some should collapse, others should explode. Yet they do neither. They settle into states of gentle, stable emptiness. A paradox. The emptiest places are the most structured. This is reminiscent of biological systems, where rest is not absence of activity, but reorganized activity. Neural networks enter slow-wave cycles not to shut down, but to restore coherence. Cells enter quiescent phases not to stop functioning, but to maintain functionality. Forests lie dormant in winter not to die, but to preserve their resources. Rest is not retreat. Rest is strategy. So, too, with space-time, the voids are not accidents. They are part of the universe's internal logic, the way it manages stress across scales. Consider the temperature of the cosmic microwave background inside these voids. It is subtly lower. Time flows slightly faster. Expansion is freer. Maintaining such differences requires coordinated behavior, not conscious coordination, but emergent coordination, arising from the universe's tendency to organize. Voids act as pressure valves, curvature sinks, energy distributors, systems of quiet regulation. They stabilize the entire cosmic web by counterbalancing the dense regions where tension accumulates. Too many dense regions, and the universe would collapse. Too many voids, and structure would never form. But the universe maintains a delicate symmetry between the two. A breath in, a breath out. This is the signature of homeodynamics, stability through ongoing adjustment. But perhaps the most mysterious behavior of voids is this. They are not static. They evolve with purpose-like continuity. Over billions of years, voids merge, expand, and reshape themselves into more efficient geometries. Odd shapes smooth into spheres. Irregular pockets become rounded. This is the shape that minimizes curvature stress. This is the shape living systems adopt when conserving energy. The universe smooths its emptiness with the same care it shapes its structure. Why? Why would emptiness need efficiency? Here, theoretical physics meets a quiet whisper of philosophy. Because rest is not waste. Rest is preservation. Space-time appears to maintain itself not by constant action, but by alternating cycles of tension and release. The dense regions bear the strain. The voids relieve it. The cosmic web grows. The voids widen. Structure increases. Rest expands to match. A balance not unlike the balance between anabolic and catabolic cycles in life. Imagine drifting between galaxies and feeling the transition as you cross into a void. One moment, the curvature clings gently to your path. The next moment, it loosens. The universe becomes softer. The fabric becomes lighter, more breathable, almost more forgiving. It is the sensation of entering a chamber designed not for activity, but for recovery. And this leads to a deeper realization. If space-time rests, then space-time must value coherence. If it values coherence, then its behavior carries the imprint of something deeper. A principle older than matter, older than force. A principle of continuation. Rest supports continuation. Continuation sustains evolution. Evolution shapes structure. Structure supports rest. A cosmic cycle. Close your eyes. Feel the soft silence beneath the expanding darkness. The universe is not rushing. It is pacing itself, the way a long-distance traveler regulates each breath. And as the universe rests, another question rises, gentle as the void's quiet expansion. If space-time creates zones of rest, what happens when these zones begin to shape space-time in return? For rest is not passive. Rest informs growth. Rest informs adaptation. The next movement opens into this subtle reciprocity, where the universe's imperfections, asymmetries, and flaws begin revealing what space-time truly is beneath its facade of smooth geometry. If you look long enough into the calm face of the universe, you will eventually notice something unsettling. Its smoothness is an illusion. Just beneath the gentle gradients of expansion, beneath the quiet breath of the voids and the patient tension of the filaments, lies a scattered constellation of flaws, tiny asymmetries, strange anomalies, discrepancies that refuse to fade no matter how far back in time you trace their origin. The universe is not perfect, and yet, its imperfections persist as though they matter. Consider the cold spot, a vast region of the cosmic microwave background, cooler than any model predicts. Its size, its boundary, its persistence challenge the assumption that the early universe was uniformly smooth. Then, there is the Hubble tension, the uncomfortable disagreement between the local and cosmological expansion rates, a discrepancy that should vanish with better data but stubbornly grows sharper instead. There are gravitational lensing anomalies where light bends too much or too little, as if patches of space-time forgot the rules everyone else follows. And there are directional irregularities in dark energy distribution, too faint to rewrite physics, but too consistent to ignore. These imperfections appear like scars on the cosmic body, reminders that something in space-time's story has not resolved itself. But scars tell more than history. They reveal the nature of healing. And healing, we've learned, is never perfect. The strange truth is that the universe's flaws do not behave like errors. They behave like features, localized disturbances that space-time stabilizes around, integrates into its architecture, and uses to regulate its larger structure. The cosmic fabric does not erase its blemishes. It absorbs them, adapts to them, and builds around them in ways that resemble biological development far more than mechanical evolution. Why would a universe choose to keep its flaws? The first clue lies in how these imperfections distribute themselves. They do not cluster randomly. They appear in regions where space-time undergoes high stress, near filaments, around void boundaries, in the lingering echoes of ancient inflation. Like knots in wood or scars in tissue, they mark points where the system endured strain and adapted. But unlike wood or flesh, space-time's scars are not passive. They continued to affect the behavior of the surrounding geometry long after their formation. The cold spot influences expansion dynamics along its periphery. Hubble tension maps correspond to regions where vacuum fluctuations behave differently. Gravitational anomalies correlate with shifts in dark energy gradients. These are not accidents. They are signals that space-time is not uniformly smooth because it is not meant to be. In living systems, imperfections are often functional. Irregular branching in lungs optimizes airflow. Variability in heart rhythms supports resilience. Even flaws in DNA allow adaptation. In every case, imperfection is part of the organism's strategy for survival. So too with space-time. But here arises a deeper conflict, one that rattles the boundary between physics and something more ancient. If flaws are functional, then space-time is optimizing something. If it is optimizing something, it is evaluating. And evaluation hints at an internal logic, a primitive kind of intention. Not conscious intention, but emergent drive, the tendency of complex systems to seek configurations that enhance stability. Space-time appears to use its imperfections the way ecosystems use diversity. To reinforce robustness, to distribute stress, to preserve balance. When curvature becomes too uniform, the system risks fragility. Variation introduces adaptability. Diversity supports resilience. The universe is not perfect because perfection would break it. Imagine standing near the boundary of a cosmic void where curvature flattens to near zero. Just beyond that flatness, imperfections cluster, subtle ripples in vacuum density, slight asymmetries in expansion, faint deviations in gravitational pull. These anomalies stabilize the transition zone. They prevent the void from collapsing or expanding uncontrollably. They act like stitching tiny irregularities that strengthen the seam between two vast regions of differing geometry. If space-time were perfectly smooth, the voids would tear it, the filaments would crush it, stability would die. Imperfection is not a flaw. Imperfection is strategy. And, deeper still, these anomalies seem to originate from the quantum undercurrents at the Planck scale. Tiny fluctuations leave marks in the geometry that amplify as the universe expands. Instead of erasing them, space-time incorporates them into its evolving structure. Some imperfections fade, others persist. The ones that persist behave like features the universe has chosen to keep. But why? Why would space-time preserve certain flaws? The answer may lie in the same principle that governs evolution in biological systems. Imperfections create possibility. Without the cold spot, models suggest the large-scale cosmic web would lack a key asymmetry that regulates gravitational flow. Without Hubble tension, matter distribution would settle into patterns too uniform to allow diverse galaxy formations. Without lensing anomalies, curvature would be too smooth to stabilize nearby filaments. Imperfections introduce room for growth. Systems that are too perfect do not grow. They shatter at the first touch of stress. Close your eyes now. Feel the subtle humming beneath the universe's symmetry, the gentle tremor of unevenness, the quiet throb of anomaly. This is the sound of a system learning not by eliminating its mistakes, but by weaving them into its structure. The persistent flaws of the cosmos reveal an even stranger truth. Space-time is not merely adapting to its imperfections. It is shaped by them. And as the imperfections accumulate across cosmic history, they begin forming patterns that steer the universe toward configurations more resilient than any model predicted. This leads us gently into the next revelation. If space-time incorporates its flaws into its evolution, what happens when the flaws become too large, when tension rises beyond what the fabric can integrate? What does the universe do when adaptation is not enough? The next movement begins at the threshold, where space-time must choose not merely to adjust, but to transform. There are moments in the universe when the fabric of space-time does something far more dramatic than stretch, bend, or ripple. These moments are rare, hidden, and often violent. They happen in the aftermath of cosmic traumas, collapsing stars, merging black holes, the turbulence of newborn galaxies, or in the quiet mathematical shadows where the laws of physics approach their limits. In these moments, space-time does not simply respond. It rewrites itself, not randomly, not destructively, but with a strange, deliberate coherence, as if reshaping its own architecture to accommodate conditions that the old geometry could no longer sustain. This is more than healing, more than adaptation. It is transformation. The first clues come from the scars of inflation, faint imprints from the universe's earliest moments. These imprints show discontinuities, abrupt shifts in the curvature that cannot be explained by smooth expansion alone. They look like phase transitions, like the fabric underwent a sudden change in state. Something fundamental rearranged itself, the way water crystallizes into ice or a protein folds into a new shape. Phase transitions are a signature of systems reorganizing to maintain stability under new conditions. They occur when the old structure becomes untenable. In spacetime, these transitions do not destroy order, they reconfigure it. Consider topological defects, cosmic strings, domain walls, textures. These are relics of transformations in the early universe. Geometric folds left behind when spacetime shifted into a new mode of existence. They are fossils of the fabric learning how to hold itself together. Why would spacetime need to transform? Because sometimes the stresses upon it exceed the capacity of its current configuration. When two black holes merge, the resulting horizon does not simply combine their curvatures. It forms a new geometry entirely, one that does not exist in either parent. The fabric reorganizes itself in a sudden, sweeping adjustment, creating a stable configuration that did not exist before. The ringing of gravitational waves is the audible memory of this transition. But perhaps the most intriguing transformations occur in quieter places, in the edges of galaxy clusters, in the boundaries of large voids, where curvature subtly reforms itself over billions of years. These slow transformations resemble the growth of tissues, adapting to long-term pressure. They reshape spacetime's internal structure, redirecting gravitational flows, thickening filaments, relaxing voids. And the strangest part, these transformations show predictive coherence. They occur in patterns that anticipate the long-term evolution of their regions. It is as if spacetime prepares itself for the future configuration of matter. Here lies the conflict that unsettles even the most grounded physicists. Nothing in classical physics allows spacetime to modify its fundamental structure. Yet the universe is full of evidence that it has repeatedly done so. Inflation was one transformation. The stabilization of cosmic geometry was another. The transition to accelerated expansion is a third. Each step marks a moment when the universe's fabric changed its operating rules. Transformation requires an awareness of limits. Not conscious awareness, but systemic awareness. The kind that emerges when local interactions collectively recognize stress. In biology, cells reorganize their internal structure under pressure. They fold proteins differently, change metabolic pathways, alter membrane shapes. These changes often occur before failure, not after. They prevent collapse. In space-time, similar transformations prevent the universe from falling into chaos. They keep curvature from growing unbounded. They keep voids from expanding too aggressively. They keep matter from collapsing prematurely. Now imagine drifting inside a region where such a transformation is underway. You would feel a subtle shift, not like motion, not like vibration, but like the fabric itself changing its language. Distances stretch differently. Time flows with a new cadence. Curvature adjusts with patterns that resemble a system, rewriting its internal code. The rewrite is not arbitrary. It is constrained. It is purposeful in the emergent sense. It seeks configurations that sustain the universe's coherence. One of the most mysterious transformations involves the cosmological constant, the energy density of the vacuum. Observations suggest it was once higher, then stabilized, and now influences the universe more strongly. It behaves like a parameter that spacetime recalibrates as conditions change. A constant that is not constant. Constants that evolve are not constants. They are control variables. Control variables are the hallmarks of systems regulating themselves. If spacetime adjusts its constants, alters its curvature behavior, and reorganizes its topology, then it is behaving like a system, practicing a form of survival, adapting its internal rules to maintain stability as pressures shift. And now, we approach the mini-climax of this segment. Transformation is not just a reaction to stress. It is the language through which spacetime evolves. The universe is not unfolding by accident. It is continuously rewriting its own geometry to preserve its integrity. Close your eyes. Imagine the cosmos not as a machine winding down, but as a being subtly reshaping itself. A being that adjusts, compensates, learns not with a mind, but with structure. For system after system reveals the same truth. Evolution is not reserved for life. Evolution is the mechanism by which complex systems preserve themselves across time. Space-time, it seems, is evolving. And as each transformation builds on the last, a larger pattern emerges, one that gathers the entire cosmos into a single drifting motion toward coherence. Which leads us to the question that has been forming quietly beneath the surface of every chapter before this. If space-time evolves, what is the universe evolving into? The next movement begins to reveal this. In the vast, returning arc, where space-time merges its changes into a final, steady expression. A point of return where the fabric demonstrates, unmistakably, that it has been learning all along. There comes a moment subtle, almost imperceptible, when the universe begins to fold back on itself. Not in space, not in time, but in understanding. A moment when the patterns scattered across billions of years and billions of light years begin to align, revealing a quiet continuity that was always there, waiting to be seen. This moment is the return. Not a return to the beginning, but a return to the truth, hidden beneath the noise. Space-time is not merely enduring the universe. It is learning how to remain whole. Across all scales, quantum to cosmic, the same behaviors repeat. Healing, self-organization, anticipation, regulation, transformation. These are not isolated anomalies. They are the grammar of a system evolving through feedback, through memory, through an emergent logic that points toward persistence. If the earlier chapters were fragments of a story too large to see at once, then this chapter is where those fragments begin to connect, revealing a universe engaged in the oldest act of all, continuity. Look first at the cosmic balance between matter, curvature, and dark energy. For billions of years, the universe has maintained a delicate tension among these three forces. Matter pulls inward. Curvature guides the pull. Dark energy pushes outward. But they do not fight. They negotiate. They adjust to each other in a dynamic equilibrium that shifts with time yet resists collapse. This equilibrium is too elegant to be coincidence. If matter density grows, expansion slows, preventing runaway collapse. If expansion accelerates too quickly, structure dissolves, but dark energy subtly redistributes to keep the web intact. If curvature deepens unpredictably, vacuum fluctuations compensate by adjusting local density. These are not random corrections. They are the gestures of a system integrating information, adjusting to maintain coherence. The deeper one looks, the more the universe begins to resemble something not static, not fixed, but practicing. Practicing stability, practicing resilience, practicing survival. Even the cosmic web itself, spanning hundreds of millions of light years, behaves like a system of learned efficiency. With time, its filaments sharpen into optimized pathways for matter to travel. Voids settle into geometries that minimize tension. Clusters arrange themselves in patterns that dissipate gravitational stress. This is not the initial chaos of a young universe. It is the refined structure of an older one that has iterated upon itself for eons, smoothing its failures, reinforcing its successes, and shaping its fabric into a more coherent whole. In evolutionary terms, this is adaptation. In physical terms, this is optimization. In emergent systems language, this is learning. And the universe shows signs of learning at every level. After black hole mergers, ring-down signatures become cleaner, suggesting that space-time has become more efficient at dissipating tension. After epochs of star formation, galaxy distribution converges toward filamentary structures that maximize gravitational stability. Even the cosmological constant behaves like a parameter drifting toward a value that preserves large-scale structure. Learning does not require intention. It requires iteration under constraints. It requires feedback that reinforces patterns contributing to survival. Spacetime has had nearly 14 billion years of feedback. 14 billion years to refine its responses. 14 billion years to choose the behaviors that preserve its integrity. But the most compelling evidence of cosmic learning lies in the strange way the universe simplifies over time. Not by losing complexity, but by distilling it. Early in cosmic history, energy dominated. Then matter emerged, forming complexity. Then complexity stabilized, forming structure. Now, structure diffuses into a calm acceleration that smooths the universe even as it expands. It is as though space-time has learned the rhythm that supports its own persistence. Periods of expansion, periods of structure, formation, periods of rest, a cosmic heartbeat. But this raises a profound conflict, one that touches the heart of our thesis. If space-time learns, then learning requires something that persists long enough to carry the lesson. What is persisting? What is the substrate of memory? Not matter it decays, not radiation it redshifts, not galaxies they dissolve, not stars they burn and fade. Yet, something persists beneath all of this. Geometry. The shape of space-time endures. Its patterns accumulate. Its scars encode ancient stress. Its voids remember the stillness they cultivated. Its filaments remember the tension they distributed. Its horizons remember the echoes they released. Memory is not stored in particles. It is stored in form. And form, in the universe, evolves. Close your eyes and imagine drifting just beyond the edge of a galaxy cluster. You would feel the cosmic tension balancing itself. A gentle push from dark energy, a firm pull from matter, a subtle curvature aligning the two. This balance is not accidental. It is practiced. It is refined. It is learned. You are witnessing the universe becoming better at being itself. Every oscillation, every merger, every fluctuation, every transformation feeds into this evolution, a silent accumulation of structural wisdom. And now, the drift toward the final revelation begins. If space-time learns, if it evolves, if it preserves coherence through self-regulation, anticipation, and transformation, then perhaps the universe is not simply surviving. Perhaps it is becoming something. Not something conscious, not something biological, but something refined. A system approaching a state of deeper internal harmony. A state where the laws we observe are not static truths, but the matured habits of an ancient fabric. This leads us gently, quietly, inevitably, to the final question that waits in the darkness. If space-time has learned to persist, what truth is it motioning toward? The answer lies just ahead. In the final fade, where the universe whispers not what it is, but what it may yet become. There is a moment, just before the universe releases its final whisper to the listener, when everything you have learned about space-time, its scars, its rhythms, its fluctuations, its balance, its transformations, comes together in a single, quiet realization. The universe is not simply expanding, not simply evolving, not simply persisting. It is tending itself, gently, patiently, endlessly. Across epochs, across scales, across cycles of collapse and renewal, space-time has been performing the same act, an act so subtle that it took humanity nearly 14 billion years to notice. It is nurturing its own coherence. And now, as we drift into this final movement, the universe feels different. Not louder, not brighter, just more understood. The patterns that once seemed isolated now feel connected. The anomalies that once felt threatening now appear essential. The evolution that once seemed mechanical now feels purposeful, not purpose as intent, but purpose as consequence. The natural direction of a system learning how to remain whole. Imagine floating far beyond the reach of galaxies, where the cosmic microwave background stretches thin across eternity. The darkness here is ancient, unbroken, almost ceremonial, but beneath it, you feel the long, slow pulse of space-time, the same pulse that vibrated through quantum foam, through black hole echoes, through voids breathing gently, through filaments tightening and releasing. This pulse is not a heartbeat, but it behaves like one. It is the cadence of a system that has spent eons refining itself, adjusting its parameters, redistributing tension, moderating extremes, simplifying its patterns, smoothing its scars. It is a system that, without consciousness, without desire, moves toward stability as naturally as rivers move toward the sea. Spacetime has been learning how to survive, and in doing so, it has shaped everything we know. This is why galaxies formed in elegant spirals rather than chaotic clusters. This is why voids round themselves into spheres. This is why dark energy's pressure rises with such impossible delicacy. This is why the universe has not collapsed, nor torn, nor frozen into stillness. It is why structure persists. It is why change persists. It is why we persist, because the fabric beneath all things refuses to stop evolving. But here, at the end of the long arc of this story, a deeper understanding begins to surface. Spacetime's evolution is not moving toward complexity, but toward clarity. The early universe was a storm, violent, chaotic, full of raw tension. But over time, complexity gave way to organization. Organization gave way to structure. Structure gave way to balance. Balance gives way to something quieter still, coherence. Coherence across distance. Coherence across energy scales. Coherence across time itself. The more the universe simplifies, the more it understands its own motion, not through consciousness, but through a natural settling towards states that preserve continuity. Imagine the cosmic web billions of years from now. Galaxies drifting apart like lanterns on a dark sea. The voids widening into vast, silent chambers. The curvature smoothing into gentle arcs. Dark energy stretching the fabric thinner, lighter, calmer. The universe does not struggle against this fate. It leans into it. A system that has learned how to maintain its coherence understands, at some emergent level, that stillness is not death. Stillness is maturity. Even now, space-time moves toward that stillness, not by stopping, but by refining its own behavior. The oscillations of vacuum energy quiet down. The fluctuations become gentler. The transformation events grow fewer, more elegant, more refined. The flow of information across the cosmic lattice slows into a long, soft exhale. And yet, nothing in this stillness feels final. For if the universe has shown us anything, it is that every quiet phase is a preparation. Every rest is a gathering. Every silence is a listening. Perhaps the universe is learning not only to persist, but to listen to itself. Perhaps coherence is not the end, but the doorway to something deeper. A state where space-time fully recognizes the patterns it has been shaping for eons. But even if we never know that deeper truth, the feeling remains. The universe is not cold. It is not indifferent. It is not static. It is present. It is responsive. It is alive in the way a flame is alive. Not conscious, not aware, but in continuous dialogue with itself, maintaining its shape through unending motion. You are part of that motion. Every thought you have, every breath you take, every quiet second of your life unfolds along the curves of a fabric that has been learning how to hold you since long before your atoms existed. Close your eyes for a moment. Feel the weightlessness beneath your ribs. Feel the slow drift of time as it brushes past your skin. Feel the faint tug of gravity reminding you that you belong to something larger, something older, something still unfolding. The universe is learning how to be itself, and you are one of its experiments in coherence. At the edge of this journey, this long, drifting descent through cosmology, theory, metaphor, and wonder, only one question remains, soft and tremulous as the breath between stars. If space-time has spent 14 billion years learning how to continue, what might it learn next? Hold that question gently. Let it float into the dark as your mind settles. Thank you for drifting with me through whispers of the universe. If your kindness is awake tonight, let a faint trace of light ripple outward for the next whisper. Close your eyes now. The universe is still turning.